As we glide toward the horizon, where even time falters, will crossing that silent threshold unveil gravity's true face, or erase us from its tail? In the silent depths of space, a journey begins. There is no rush, only the calm embrace of the stars around us. As we drift through the cosmic expanse, a shadow looms in the distance, a darkness that calls us toward its hidden secrets. The silence is profound. Even here, in this void, the universe seems to hold its breath. There is no thunder, no storm, only the gentle whisper of space-time guiding us onward. Each heartbeat resonates with the slow ticking of the cosmic clock, measuring out the moments of this peaceful descent. We float as if underwater, weightless, moved only by the faint pull of gravity. No sound travels this far from any world or wind. The only melody is the distant hum of cosmic radiation, subtle and soothing, barely a whisper in the quiet. In this emptiness, even time seems to slow. We notice that around us, the very fabric of space-time is quietly stretching and bending, as though a gentle tide were pulling us steadily inward. The universe here feels both infinite and intimate, as if we have slipped into a secret corner of creation, cradled by invisible currents. There is a stillness to this descent that is almost sacred. No light flashes past, only the soft glow of faraway galaxies and the steady pulse of starlight. We are small observers in a vast, indifferent darkness. With each silent second, the darkness feels deeper, more mysterious. It is a dark elegance, a beauty in emptiness, and with it comes a sense of calm. Here, where nothing can be heard, the pull grows subtle. We realize we are falling, though there is no sound or scream, only the hushed acceptance of the unknown. As we fall, the stars stretch and swirl in a quiet dance. The cosmos around us is vast and empty, but it moves ever so slightly. Space itself seems alive, curling inward around something we cannot yet see. We understand that behind this gentle motion is gravity's secret. It is not something we can see directly, but we feel its presence in every drifting moment. Heavier objects, stars and planets, tug on space-time, creating currents that guide our path. In this silent descent, a force as old as time itself begins to make itself known. It is not something we can see directly, but we feel its presence in every drifting moment. In this silent descent, a force as old as time itself begins to make itself known. All at once, we sense the presence of something powerful, an invisible grace that cradles us as we fall, enveloping us in a strange embrace. It is a force so gentle that it almost feels tender, yet so enduring that nothing in the universe can escape it in the end. We allow our mind to wander as we continue. We recall other journeys on Earth, a leaf falling in a forest, the slow drift of a feather on a gentle breeze, the quiet flow of a river under moonlight. These echoes of calm show us that even in the darkness of space, a natural rhythm exists. Gravity is that rhythm here. It draws us with unwavering intent, but not with violence. It holds us close, like a parent might hold a child tightly, but tenderly. In the absolute emptiness, that embrace is reassuring. It takes us by the hand and guides our steps, even as we lose our footing in the void. Somewhere ahead, beyond our sight, an abyss waits. We do not know its shape or its size. It cannot be illuminated by any light, and yet it exerts its influence like a magnet. This is the abyss in our story, and we are travelling toward it. We do not approach in fear, but in awe. It is a pilgrimage of the mind. Every instinct and every law of nature is about to be tested here. Yet the prelude is peaceful, as if nature herself is whispering, "Be ready." A faint glow from afar hints at what lies beyond our path. Nebulae and distant suns cast gentle light, painting the darkness in soft shades. But this light too begins to distort around us, caught in the steady pull of something immense. Light rays bend in subtle arcs, revealing that even light cannot maintain a straight course near this place. We can feel that what awaits is not simply more darkness, but a doorway to a singular mystery. As we glide silently ever closer, a quiet question forms in our mind. What is this abyss we are approaching? If stars have beginnings and ends, how does an ending begin? We wonder what forces could have carved out this silence. We prepare ourselves with tranquil hearts to seek answers. And in that moment, our journey turns inward as much as outward. The silence deepens. Our descent continues. Guided by an ancient embrace, we are about to truly understand. Our eyes, imagination in this case, try to see the silhouette of the abyss. We see only darkness against darkness, a horizon in the black. There are no stars to show us the way now. The only compass is the feeling in our chest, the weightlessness and the gentle pull, as though we are cradled by an invisible hand. This silent descent feels natural. It is part of a larger harmony, like the closing of a circle that began with the birth of stars. Behind us, the remnants of the cosmic sea continue their quiet dance. Clouds of gas drift slowly, tumbling in patterns determined by gravity. Faraway suns glimmer softly, unchanged by our passage. We are but spectators to this grand ballet. And yet, we are also participants. Our own body is now part of the cosmic story, pulled by the same force that bends the starlight around us. In the end, everything we see and cannot see is connected by this force. The silence speaks of unity. In this gentle dark, we hear something after all. The ticking of our own curiosity, growing louder in the quiet. Every moment is a breath. Every passing second, a heartbeat, syncing with the universe. The silence of our surroundings allows our thoughts to become loud. We feel the gravity of the moment, not just as a force, but as an idea. It is an idea older than any civilization, one that shaped galaxies and will shape us too. The darkness reaches out for us now, engulfing our view with its calm intensity. We can sense it, not as something to fear, but as an old friend inviting us to learn. And as we let go of the last glimpses of light, we realize what has been holding us all along. In the silence, in the darkness, it is clear. Gravity's embrace is why we have come here. It is the force that guided our descent. It is what shapes the silence itself. And so, in this silent descent, our journey prepares us to truly understand that force, just as it has held our fate. Close your eyes and remember the story of the apple. Long ago, it fell from a tree and sparked an idea. the same force pulls on Earth and on the Moon. We pick up that tale here. Newton imagined that every mass in the universe attracts every other mass, that apples and planets obey the same gentle law. He gave us a simple rule. Gravity's pull depends on mass and distance. Under that rule, the apple falls, rivers run downhill, and planets circle their stars. Galileo showed that all objects, whether heavy or light, fall the same way if air is removed. A hammer and a feather drop together. Gravity does not play favourites. It is the universal handshake that pulls Earth's rains to the sea, just as it tugs on the Moon at night. On Earth, we feel gravity as a constant companion. It keeps our feet on the ground and makes rivers flow downhill. In childhood, perhaps you saw that if you roll a ball, it always travels straight down the slope, as if an unseen hand guides it. Submarines dive or ascend in water. But on land, gravity keeps mountains rooted and makes waterfalls descend to meet the valley. We once believed gravity was a force transmitted through empty space, until Einstein had a thought experiment. What if you were falling in an elevator? You would feel weightless. He realized that free fall under gravity is indistinguishable from floating in space. In Einstein's 1916 picture, gravity became geometry. He taught us that a massive object tells space how to curve, and space tells objects how to move. Imagine space as a stretched rubber sheet. Place a heavy ball on it, and the sheet sags. A marble rolled nearby will spiral toward the heavy ball, not because of a mysterious pull, but because it follows the curved surface. In the same way, planets orbit the Sun by following the warps in space-time that the Sun creates. Even time itself joins gravity's dance. Clocks closer to a mass tick slower than those farther away. Satellites high above Earth feel a weaker gravity, and their clocks tick a bit faster. We correct for this in GPS so our navigation remains accurate. All around us, every drop of water, every gust of wind, every heartbeat knows gravity. It is gravity that shepherded the dust of the early universe together into the first stars. Gravity gathered clouds of gas and dust to form our own sun, and then coaxed the planets into their steady paths around it. A star is born only because gravity pulled its raw material together until nuclear fires ignited. In our calm exploration, all this knowledge coalesces. From the prosaic apple to the cosmic ripple, gravity's embrace is everywhere. Now, standing on the threshold, we ask, if gravity can tangle time and bend light, what wonders lie at its very limits? In the cosmos, the final test awaits at the heart of a dying star, where the curvature of space-time becomes extreme. Each gentle step here has prepared us to meet gravity at its breaking point. In Newton's time, the idea that one law could describe both falling apples and orbiting moons was revolutionary. People in the 1600s had always observed gravity's effects, but Newton gave us the language to understand them. He wrote that everything in the universe pulls on everything else. That statement set the stage for centuries of astronomy and physics. It meant that the moon stayed in orbit around Earth by the same invisible tug that kept our feet on the ground. It meant planets have their paths traced by the same gentle pull. In Newton's day, gravity acted at a distance without any visible connection, almost like magic. Even Newton wondered if there might be an unseen medium filling space, but he was satisfied that his formulas worked in practice. With Newton's gravity, we could send probes to other planets and predict their journeys, as if every star and comet danced under one universal rule. And yet, even he knew there was more to learn. Fast forward a century. Albert Einstein came along and asked whether falling apple and accelerating elevator were the same experience. He concluded they were. His great insight was that gravity is not a force pulling directly, but the curvature of space-time itself. In Einstein's view, the presence of mass warps the geometry around it. John Wheeler once summarized it. Space-time tells matter how to move. Matter tells space-time how to curve. A stone thrown upward and the ocean tides of the moon around Earth are both due to the same cosmic contour. We have lived our entire lives under gravity's influence without noticing its profundity. Every object from dust mites to mountains, from Earth to galaxies, responds the same way. The pull that lets us walk, that makes trees lean towards sunlight, that keeps our atmosphere wrapped tight, is the same that shapes the orbits of planets and guides comets on their long journeys. It is gravity that will ultimately carry us safely into the darkness ahead. In this silence, as we descend, we know the path of our fall is not random, but guided by this known force. Our peaceful reverence for gravity's law prepares us to meet its deepest mysteries head on. As our understanding of gravity deepened, some asked if nature held even more extreme secrets. In 1783, English scientist John Michell pondered a startling idea. He imagined a star so massive that the escape velocity from its surface would be the speed of light. In Newton's theory, this was possible if a star were dense and large enough. Michell reasoned that such a star would not be visible to an outside observer. It would be a dark star from which light could not escape, a cosmic object cloaked in darkness. In effect, it would be a star made invisible by its own gravity. Michell went further. He suggested that if such a dark star had a bright visible companion, the visible star might circle as if responding to an unseen partner. An observer might see one star wobbling around and think there are two, until realizing one partner was hidden. In this way, we could infer an invisible star's existence. This was a visionary idea, though at the time, astronomers had no means to test it. Michell called these hypothetical objects dark stars, and he painted a theoretical portrait of a star so heavy that even light could not climb out of its gravity well. Almost at the same time, the French mathematician Pierre-Simon Laplace considered a similar notion. In the 1790s, he speculated in his textbook that a sufficiently massive star could trap light by its own gravity. At the time, light was still thought of as particles, and under Newton's law, this made sense. Laplace wrote that such a star would be invisible. However, as the wave theory of light gained acceptance, this idea was quietly dropped by most scientists. Newton's particle picture faded, and with it, the concept of dark stars fell out of favor for a time. 2 centuries later, Einstein's revolution gave a more complete picture of gravity. In 1916, Karl Schwarzschild, even while serving on the Russian front, found an exact solution to Einstein's field equations for the spacetime around a spherical mass. Remarkably, Schwarzschild's solution implied a special radius. If a star collapsed within this radius, even light could not escape. This critical surface we now call the event horizon. Schwarzschild's math was abstract, but it confirmed that Michell's dark stars could indeed exist in Einstein's universe. Astrophysicists in the 1930s began to piece together a fuller story. Indian scientist Subrahmanyan Chandrasekhar found that there is a limit to how massive a dead star can be if it's supported only by electron pressure. Beyond about 1.4 times the Sun's mass, a white dwarf cannot hold itself up. Young Chandrasekhar even sailed to England in 1930 with these calculations and presented them to Arthur Eddington. The result was dramatic. Eddington could not accept the idea of unlimited collapse. At a meeting, he denounced it as stellar buffoonery. Chandrasekhar's results suggested that heavier stars would inevitably collapse beyond what was then known. Although Eddington dismissed it, Chandrasekhar's conclusion was later proven correct. Nature does allow the collapse to continue. In 1939, J. Robert Oppenheimer and his student, Hartland Snyder, took the idea further with Einstein's theory. They showed mathematically that if a star's core exceeds a certain mass, no force can halt its collapse. To an outside observer, such a collapsing core would appear to slow and freeze at its event horizon, fading from view. Inside the horizon, however, everything would race inward toward the center. In effect, gravity wins completely, crushing the core beyond any known limit. While the word black hole had not yet been used, Oppenheimer's work made it clear that general relativity permitted such objects to form. The concept of a black hole became more concrete mid-20th century. In 1967, physicist John Wheeler coined the term during a lecture, capturing the imagination of scientists and the public. Around that time, mathematician Roger Penrose proved a theorem that singularities, points of infinite density, would generically form during such a collapse. Slowly, what once was rejected became accepted. Black holes were recognized as an inevitable consequence of gravity's laws when pushed to the extreme. The event horizon is a subtle notion. It has no hard surface, no sound or light. One way to imagine it is like the edge of a waterfall in a calm river. From a distance, you see the river flowing, but at some invisible line, the water begins to rush over and vanish from view. As one approaches that line, nothing special is felt. Only inside does the nature of things change irrevocably. In the same way, an observer crossing a black hole's horizon would feel nothing unusual at that boundary, yet from that point on, all paths lead inward. And so, in this quiet reflection, we are ready to move forward. We began this chapter in thought, tracing black holes from a curious prediction to a firm prediction of relativity. The question now is, where do we find them in reality? Our next step is to watch the life and death of stars and see how, through natural processes, the universe may create the very abyss we have been talking about. In the chapters to come, we will explore how dying stars create the darkness we have been studying, and how astronomers discovered the hidden silhouettes of these cosmic giants. A star lives in balance, a gentle equilibrium between the crushing weight of its own gravity and the explosive pressure of nuclear fusion at its heart. For most of its life, a star quietly fuses hydrogen into helium, producing energy that shines and holds the star up. The sun, for example, has shone steadily for billions of years, its core a furnace burning at immense heat, but in perfect balance with gravity's pull. When you look up at the night sky, the light of each star is a sign that fusion and gravity are dancing in harmony. Yet every star's fuel will eventually run out. In a star much larger than our Sun, say 10 times or more, the core will burn its way through hydrogen, then helium, then heavier elements like carbon and oxygen. Eventually, it forms iron. Iron is the dead end of fusion. Fusing iron consumes energy rather than releasing it. At that moment, the outward push from fusion disappears. Gravity, which has been patiently pulling all the while, suddenly takes over. The star's core begins to collapse in on itself in freefall. This collapse happens in the blink of an eye, on cosmic timescales. The core shrinks and heats rapidly. When it reaches nuclear densities, as dense as an atomic nucleus, it stiffens very briefly and bounces. The outer layers of the star crash into that rebounding core, and the energy released blasts the star's envelope outward. The star explodes as a supernova, a brilliant flash that can outshine a galaxy for a few weeks. The ejected material, atoms forged in the star and in the explosion, is flung into space. In that instant, the star has given back to the cosmos, scattering elements that will later form new stars, planets, and perhaps life itself. After the fireworks fade, all that is left of the star is its compact core. What becomes of that core depends on its mass. If the core is not too heavy, less than roughly 3 times the mass of the Sun, it can settle into a neutron star, a city-sized sphere of neutrons so dense that a teaspoonful would weigh billions of tons. But if the core's mass is greater, even neutron pressure cannot stop the collapse. Gravity wins completely. The core continues to shrink beyond any known limit, and a black hole is born. In that final collapse, nothing holds it up. All the star's mass is packed into an ever smaller volume. At the very instant a black hole is born, a remarkable change occurs. An event horizon forms. This is an invisible spherical boundary around the collapsed core. Outside this horizon, the universe behaves almost as before, though gravity is now overwhelmingly strong. Once any matter or light passes inside this boundary, however, it can never come back. For outside observers, the newly formed black hole seems to appear suddenly and silently. Time itself stretches near the horizon. Light escaping from just outside the horizon grows redder and dimmer, fading away. It is as if the star's image slows, reddens, and finally vanishes, plunging beyond a cosmic veil. For the material that falls in, the experience is utterly different. From that frame of reference, nothing dramatic happens at the horizon itself. The material simply continues inward. Once inside, all roads lead further inward toward the singular core. The star has given birth to an abyss, a region of space-time from which no escape is possible. The gentle pull that governed the star's life has become an inescapable grip. The star that once shone has become a shadow, its history now encoded in an invisible remnant. Thus, a star's death is also the birth of a black hole. The brilliant supernova fades, and at its core remains a silent darkness. At the center of that darkness lies the event horizon, a point of no return. It has arrived without fanfare, as nature's final victory of gravity. The once familiar star now survives only as a whispered memory at the edge of the void. We have seen how nature creates these dark objects when massive stars die. Our exploration now turns to how we might find and study them. Black holes are invisible, but their presence can be revealed by the effects they have on their surroundings. In the next chapter, we will journey with astronomers as they hunt for the signs of these unseen forces, using light, X-rays, and even the fabric of space-time itself. We drift through the silent void of space, our vessel surrounded by endless night. Stars speckle the darkness in every direction, distant suns shimmering like tiny beacons. As we journey onward, a subtle change begins to take shape in the starfield ahead. The patterns of starlight warp and bend in an uncanny way, as though seen through rippling water. Far in the distance, something invisible is tugging at the light itself, a sign that we are approaching the abyss. Ahead of us lies a place where gravity reigns supreme, a region of space so intense that nothing can escape its grasp. Though we cannot yet see the black hole directly, we feel its presence. It makes itself known in how it distorts the world around it. Light from stars behind this hidden giant curves around an unseen center, creating a faint halo. The gravity is bending space itself, acting like a cosmic lens that warps the scenery. In the middle of that distortion is a patch of darkness where no starlight shines. It is there that the black hole waits, a void lurking in plain sight, revealed only by the cosmic mirage it casts. Our spacecraft glides closer, engines quiet, as if nature itself has hushed in anticipation. With each passing moment, the gravitational pull of the black hole grows stronger. It's not a sudden jolt, but a steady, relentless tug, like an ocean current drawing us in. We are still far enough away that we feel weightless, free falling toward this mysterious mass. But even now, instruments aboard detect the growing influence of gravity. Navigational readings shift, showing our trajectory curving inward, caught in the black hole's powerful embrace. In this emptiness, there is no up or down, no sense of scale, only the deep black ahead that grows wider and deeper. The stars that once lay scattered randomly now appear to swirl around one central region of darkness, as if outlining a great invisible whirlpool. The closer we get, the more distorted our view becomes. Space itself is curving steeply here. Straight lines of light now travel along bent paths. We are witnessing Einstein's theory of general relativity in action. The massive object ahead is warping spacetime, and everything, light, our route, even time, is subject to its influence. Drifting ever closer, we cross an unseen threshold where the black hole's gravity dominates the environment. We have entered the black hole's realm of influence, a kingdom of warped space. At this distance, even if we tried to turn back, it would take enormous energy to break away from its pull. We carry on, drawn by curiosity and by nature's inexorable force, deeper toward that patch of darkness. The sensation is eerily calm. There is no violent shudder, no dramatic change in scenery all at once. Instead, there is a slow, inevitable change, a feeling that we are descending, though there is no ground or floor beneath us. With each passing mile, the blackness ahead grows larger, expanding from a tiny blot to a vast shadow. It's as if night itself has swallowed a piece of the universe ahead. Around this growing darkness, the stars now form strange arcs and streaks. Points of light smear into curved lines, looping over and under an empty center. These distortions are not tricks of our eyes, but real bending of light by gravity. We are now close enough to clearly observe how the black hole bends the light of the universe. It's as if space is a fabric being stretched and wrapped around something we cannot directly see. We glance back at the familiar stars behind us, and then forward to the emptiness ahead. The contrast is profound. Behind, the cosmos looks almost normal, an expanse of glittering lights on dark velvet. We can see the broader galaxy around us, perhaps a milky band of countless distant stars, carrying on as usual at the fringes of this cosmic whirlpool. That makes the scene even more surreal. Ahead, the view is dominated by a great black pit outlined by the contorted light of background stars. It feels as though we are approaching the edge of reality, a threshold between the known universe and a realm beyond understanding. As we move closer still, a faint glimmer begins to encircle the darkness ahead. What began as subtle distortions in starlight now evolves into a thin, ghostly ring of light. It wavers around the black shadow at the center, marking where light itself orbits and dances before vanishing inside. This ethereal halo hints at the turmoil that must be taking place further in. We realize we are on the outskirts of a cosmic maelstrom, not yet close enough to see it fully, but close enough to sense its presence. All remains quiet aboard our ship. There is no air in space to carry sound, no roar of engines as we mainly coast under gravity's spell. The only sounds are our own breaths and the soft hum of life support systems. It's a strangely tranquil journey towards something so forbidding. In the silence, one cannot help but feel a mix of awe and trepidation. We are journeying to the abyss, approaching a place where the normal rules of physics will be pushed to their limits. Still, the beauty of this moment is undeniable. The warped starlight around the black hole twinkles in gentle ribbons. Cosmic rays and high-energy particles, accelerated by gravity, create occasional flashes as they zip by. Perhaps the dying light of atoms being torn apart. Against the deep dark, these sparkles are like fireflies, swirling around a giant invisible beast. The sight is both peaceful and unsettling. Peaceful in its silence and grandeur, unsettling in knowing what that darkness represents. Gradually, the faint halo ahead intensifies. From a delicate ring, it widens into a more substantial band of light encircling the darkness. We realize that this is more than just bent starlight. We are beginning to see the outer edges of the black hole's accretion disk. The journey to the abyss has brought us near the material that orbits the void. Like a distant sunrise, a soft glow rises ahead, heralding the brilliant beacon of energy that surrounds many black holes. Our eyes widen, and a surge of adrenaline mixes with awe as the glow resolves into a clearer sight. The cosmic whirlpool is truly coming into view. The black hole we approach is not a lonely, silent ghost. It is feeding. Matter from its surroundings has been drawn in, forming a swirling disk that we can now clearly perceive. From our vantage, the disk appears slightly tilted in space, not just a flat ring, but an ellipse slanting before us. It pours light into the darkness, shining brighter as we draw nearer. What was once a faint, hazy band of light now reveals texture and motion. That broad, luminous ring wrapping around the black heart of the black hole is the accretion disk. It is breathtaking in scope and brilliance. The disk's light is not steady, but flickers and shimmers, a sign of turbulent activity. Closer to the black hole, the glow intensifies into a brilliant, searing white arc. Farther out, it softens into a dimmer golden haze. We can imagine the colours shifting through the spectrum, deep reds and oranges at the cooler outer edges, graduating to dazzling blue-white in the blazing inner region where the energy is greatest. As we approach, the sheer scale of this structure becomes apparent. This disk of gas and dust is enormous, spanning unfathomable distances across space. It could be millions of miles across, a sprawling whirlpool of cosmic material. Yet from afar, it looked delicate, like a ring of satin around a shadow. Now, up close, we sense its immense power and mass. We also sense its motion. It spins at tremendous speeds. The inner edge of the disk orbits nearly at the speed of light, completing a revolution in mere minutes. Out near the outer edge, an orbit might take days or months. From our perspective, we see evidence of this motion in the patterns of light. Bright regions that shift and drift, marking clumps of gas whipping around and plunging inward. We still keep a respectful distance, skirting the outer fringes of this tumultuous disk. Even here, the environment grows more intense by the minute. Occasionally, specks of interstellar debris streak past our vessel, accelerated by the gravitational field. These tiny motes of dust and rock, normally harmless in space, zip by at such high velocity that they would punch through metal. It's a reminder that this region is far from empty. It is alive with energetic particles and radiation. We have effectively entered a cosmic storm of swirling matter. The cosmic whirlpool draws us closer to its heart, and with each passing moment, new details snap into focus. The accretion disk is not a uniform, placid ring. It is dynamic and violent. We can make out spiral patterns within it, as if great waves or arms of denser gas are coiling toward the center. Bright flares erupt here and there as material crashes into other material, releasing bursts of light and heat. Perhaps these flashes are the last visible moments of something that once was, the shredded remains of a star, or the guts of a disrupted planet, igniting as they spiral inward. Every such flare is a beacon, a reminder that this disk is in constant upheaval. Looking closely, one side of the disk appears a bit brighter than the other. As we observe, we realize this is due to its rotation and the effects of relativity on light. The side of the disk that is spinning toward us has its light slightly boosted in energy, a phenomenon akin to a Doppler shift, where approaching waves are compressed. The side spinning away has its light diminished, waves stretched out. The result is subtle but noticeable. One side of the glowing ring shines a touch more intensely. The physics behind this is complex, but it clearly tells us which direction the disk rotates. We marvel at this natural demonstration of relativity and motion on a cosmic scale. Our gaze wanders beyond the disk itself, and we notice something extraordinary above and below it. Extending from the poles of the black hole, perpendicular to the disk, are colossal jets of energy. They are like twin searchlights in the cosmic night, stabbing outward from the chaos of the disk. At first, we saw them only as faint columns from afar. Now, as we adjust our trajectory for a clearer look, they stand out with awe-inspiring clarity. Each jet is a stream of particles accelerated to nearly the speed of light, confined into a narrow beam by the black hole's intense magnetic fields. They are not continuous lasers of light, but rather fountains of matter and energy. They glow because the particles within are so energetic that they emit light across the spectrum, from radio waves to visible light to X-rays. In places, the jets appear to shine with a bluish tint, indicating their fierce, high-energy nature, though much of their light is beyond human vision in the gamma-ray range. We trace one jet with our eyes as it pierces the darkness above the disk. It remains remarkably straight and collimated, narrow, for an immense distance. These jets can reach astonishing lengths, in some cases hundreds of thousands of light years, far beyond the galaxy that hosts the black hole. The giant galaxy M87, for instance, harbors a supermassive black hole that drives a jet visible across 5,000 light-years of space, a pale, bluish spear seen in telescopes. The jets carry away tremendous amounts of energy and matter into intergalactic space. It is humbling to behold, a cosmic geyser blasting out from the vicinity of the black hole, likely fed by the magnetic and rotational forces deep near the core of the disk. The origin of these jets is still somewhat mysterious, even to the greatest minds back on Earth. We know they spring from the inner regions of the accretion disk, just outside the event horizon, where magnetic fields are twisted into knots by the spinning disk and perhaps by the rotating black hole itself. Somehow, a fraction of infalling material gets caught in those magnetic field lines and is flung outward instead of inward, accelerated to near light speed. The result is what we see now. Matter that was destined to fall in is instead shot out in two opposite directions along the poles, painting the darkness with twin beams of light. Watching those jets, we feel a profound sense of the black hole's influence. This single object, through its disk and jets, is affecting regions of space unimaginably far away. One of those jets could eventually slam into distant clouds of gas light years out, stirring or heating them. In fact, astronomers believe that such jets can both trigger and impede the birth of new stars in those clouds. Black holes, through these jets, can shape the evolution of entire galaxies. We recall images of giant radio lobes billowing at the ends of jets in distant galaxies, structures so large they defy comprehension. Now we are witnessing the engine that drives those colossal cosmic structures. As we continue our approach, our ship's trajectory takes us closer to the plane of the accretion disk to better survey it, all while maintaining a safe berth. We angle just above the disk plane, allowing us to gaze down into it without plunging through its densest parts. From this viewpoint, the disk stretches beneath us like a vast, luminous whirlpool in space. The central black circle of the event horizon's shadow is clearly visible at the disk's center, a yawning mouth surrounded by a brilliant brim of orbiting matter. Against that bright backdrop, the very center appears truly black. In April 2019, humanity got its first glimpse of such a scene when the Event Horizon Telescope captured an image of a black hole's shadow in galaxy M87, a glowing ring of gas surrounding a dark center. Now, we have become the camera, floating just above a black hole's disk and seeing that phenomenon directly with our own eyes. The jets, now to our left and right, above and below in an absolute sense, continue to beam outward. We see the upper jet projecting into space above the disk and the lower one firing below in the opposite direction. Both remain tight near the black hole and gradually widen farther out. Up close, they might be thin as pencils of light, but as they travel thousands of light years, they fan out into enormous plumes, each potentially ending in a billowing cloud of energized gas far away. Though we cannot see those distant termini from here, we know that to a far-off observer, those jets would be among the most striking beacons of this black hole's presence, perhaps visible as intense radio sources, or as flickering gamma-ray bursts, if one were aimed our way. The light from the disk bathes our spacecraft in a steady glow. If we were to step outside now, an impossibility without extreme protection, we would be bombarded by radiation that could quickly be fatal. X-rays from the hot inner disk and bursts from the superheated corona, a halo of high-energy plasma above the disk, flood this region. Even inside our vessel, instruments register the onslaught. We rely on our shielding. Without it, this journey would end swiftly. It's ironic that what makes the black hole visible and beautiful, this shining disk, is also what makes it so dangerous to approach. We are like moths drawn to a flame. Without our protective cocoon, we would be incinerated by the light we admire. Yet here, cocooned and safe for the moment, we can appreciate the spectacle in relative peace. The disk's radiance is our false daylight in the endless night of space. We watch the swirl of matter below, as one might watch storm clouds from above. It is mesmerizing to see cosmic forces at work on such a scale. Waves of glowing gas spiral inward, disappearing one by one into that central darkness. Each wave, each swirl, represents uncountable atoms. perhaps the remnants of long-ago stars or planets, all meeting their fate as they plunge into the unknown. This leads our thoughts to the inevitable question: what happens to all that matter as it falls all the way in? We know that once material crosses a certain boundary around the black hole, it is lost to the outside universe. But is it truly gone in every sense? It does add to the black hole's mass, making the black hole ever so slightly bigger, its gravity stronger. And perhaps some of it gets transformed and redirected into those jets, returned to the cosmos in a different guise. In a sense, the black hole and its disk are part of a vast cosmic recycling process, devouring matter and energy in one form, releasing energy in another via jets and radiation, and storing the rest behind an invisible veil. As we prepare to draw even closer to the heart of this system, we fortify ourselves for what comes next. Up to now, we have been observers, hovering near the outer regions, beholding the spectacle of the accretion disk and jets from a relatively safe perch. But ahead lies the ultimate boundary, the point of no return, the event horizon lurking at the very inner edge of that brilliant disk. Everything we have seen so far, as extreme and exotic as it is, still obeys the usual rules of our universe, in that it can be observed and escaped from. We have witnessed matter heating, glowing, and even being ejected in jets. But now we are poised to approach the region where matter and light disappear entirely from view. Before we reach that final edge, we take one more sweeping look around. The disk beneath us, the stars far beyond, distorted into arcs, the majestic jets reaching outward. It is a scene of almost incomprehensible grandeur. We commit it to memory, knowing that as we venture further, such a clear view of the outside world may soon be lost. In a way, this is the last sight of the universe as we've always known it, full of light and structure, accessible to observation. Beyond the edge ahead, we enter a place where our view, our instruments, and even the flow of time will behave in ways we have never experienced. With equal measures of wonder and solemnity, we turn our gaze to the central darkness and prepare to take the next step toward the event horizon itself. We are now on the threshold of the black hole's ultimate boundary, the event horizon. This is the point of no return, the invisible line around the black hole beyond which nothing that crosses can ever come back. Our view of the accretion disk has shown us where this boundary lies. At the inner edge of the glowing disk, there is that sharp cutoff into pure darkness. That is the silhouette of the event horizon's shadow, a tangible hint of an intangible surface. We hover here for a moment, engines holding us just outside the invisible boundary, taking time to steady ourselves and reflect on what lies ahead. A tremor of apprehension passes through us. It's only natural, standing on the threshold of the ultimate unknown. But alongside the fear is profound wonder. This is what we came for, to cross into a realm no one has witnessed directly. We double-check our resolve and our instruments. Everything urges caution, yet our curiosity compels us forward. In this quiet pause, we acknowledge the gravity, in every sense, of what we are about to do. Crossing an event horizon is something no spacecraft or person has ever done and returned to tell the tale. By all the known laws of physics, return is impossible beyond this point. It is a one-way door to the deepest unknown. Interestingly, the idea of such a one-way door predates even modern physics. As far back as 1783, an English scientist named John Michell hypothesized about dark stars, whose gravity would be so strong that light could not escape. It took Einstein's theory of gravity, general relativity, to fully understand this phenomenon. In 1916, physicist Karl Schwarzschild calculated that a sufficiently compact mass would indeed form an inescapable sphere. Now we stand at the very threshold of what those early thinkers could only imagine. The event horizon is not a physical surface like a planet's crust or a star's fiery skin. It's an invisible spherical shell in space around the black hole, more like an imaginary membrane marking where escape velocity equals the speed of light. If you are outside this sphere, at a safe distance, you could in principle fire your engines or exert some force to escape the black hole's gravity. But if you are exactly at the horizon, you would need to move at the speed of light to break free. Since nothing can go faster than light, not even the fastest rocket or laser beam could escape from that point or from any closer in. Whatever passes through the event horizon is doomed to stay inside it, even light itself. To better grasp this moment, we picture another analogy for what we're about to do: a waterfall or a whirlpool. Imagine space as a river flowing towards the black hole. Far from the hole, the current is gentle. A spacecraft can paddle upstream and get away. Closer in, the current speeds up. At the event horizon, the flow of space toward the black hole is so fast that not even light, the fastest thing in the universe, can swim against it. It's like reaching the edge of a giant waterfall. Once you pass the lip, no amount of paddling or power will save you. You are going over. We feel that we are at that very lip now, at the brink of a cosmic Niagara. Our onboard clocks and instruments confirm extraordinary effects as we hover here. Light from the accretion disk and from the wider universe is now severely warped and reddened. If we shine a laser beam forward, toward the black hole, it simply vanishes, carried away by spacetime into the abyss. If we aim a beam outward, back toward the stars behind us, we notice it struggles too. The beam's frequency shifts, its energy sapped as it climbs out of this deep gravitational well. This is gravitational redshift in action, light losing energy, becoming redder and weaker as it escapes strong gravity. Hovering so close to the horizon, even our outgoing radio signals would be lethargic, slowed, and stretched in wavelength by the time they reach distant ears. We take a deep breath. It's now or never. Gently, we cut our engines and let gravity have its way. Our ship slips past the invisible boundary. In that instant, nothing dramatic seems to happen physically. There is no jolt or flash, no sense of crossing through a membrane. The event horizon is, after all, not a tangible barrier, but a location in space-time. Yet, symbolically, everything has changed. We have done the unthinkable. We are now inside a black hole. Remarkably, since we are in freefall, we still feel weightless at the moment of crossing. The gravitational force pulls evenly on every part of us, so there's no strong sensation of being dragged. It's just like floating. If the black hole is large enough, as ours is, crossing the horizon can be quite gentle, with no immediate drama at all. Indeed, because we're freely falling, we don't feel the full brunt of gravity, only the differences in gravity across our bodies. For now, we continue to float, as if nothing were amiss. The outside universe, however, is now forever cut off from us, and we from it. From this moment on, any light or signal we emit will not reach the world we came from. To the universe outside, we effectively cease to exist as distinct entities. The black hole will simply remember us by the small boost in mass, and maybe a slight change in its spin. Indeed, from the outside, one could describe the black hole only by a few properties: mass, spin, and electric charge, if any, and nothing more about what it contains. A colourful phrase physicist John Wheeler used captures this. Black holes have no hair, meaning beyond those basic attributes, a black hole gives no hint of the complex details, the hair, of everything that has fallen in. If someone were watching from a safe distance, they would never actually see us cross the horizon. Instead, they'd observe our ship approach that boundary and then appear to slow down and hover just at the edge. We would seem to move more and more sluggishly. Our image would linger there, increasingly red-shifted, turning dimmer and redder, until it faded away into invisibility. To that outside observer, it would look as though time had stopped for us at the event horizon, as if we were a frozen, ghostly image on the cusp of the black hole. Our fall, from their view, would take literally forever. But here on the inside, time flows normally, and nothing of that sort is noticed. We continue to experience every second. Crossing the horizon felt like nothing special, just the continuation of our smooth descent. In fact, up until now, our freefall was deceptively serene. We felt weightless, as though gravity's grip were absent while it was holding us. Only the subtle stretching across our ship, the tidal forces, hinted at the immense power at play. If the black hole were smaller, tidal forces would already have been ripping us apart. But in this supermassive giant, the horizon crossing itself is gentle. We note this fascinating fact. The most extreme boundary in the universe can be passed without fanfare, even while it remains an impassable barrier to the outside world. Now that we are inside the event horizon, our perspective on the universe alters profoundly. Looking outward, back toward where we came from, we no longer see the wide expanse of stars and the disk as we did before. Instead, light from the outside is strangely concentrated and blue-shifted, compressed into a shrinking patch of sky directly behind us. It's as if the universe we left is being squeezed into a little luminous oval, far, far above. And even that light is rapidly fading as we plunge deeper. Ahead of us, in the direction of our fall, lies only darkness. It's not the ordinary darkness of space peppered with distant stars. It's an absolute dark, because no light from deeper inside can find its way out for us to see. Everything ahead falls faster than light now, carrying any photons with it inward. We find ourselves in a realm where space and time themselves feel turned inside out. In some sense, the roles of space and time swap inside a black hole. The pull inward is no longer just a direction in space that we might choose or resist. It's an inevitable march, much like time. We cannot stop ourselves from moving inward any more than we can stop time from advancing. In fact, going inward is like moving forward in time for us now. Unavoidable. This realization is sobering. We are on a one-way route deeper in, as inexorable as the ticking of a clock. And yet, despite the profound change in our situation, our experience of time locally is still steady. We still feel seconds ticking by at the same rate as before. It's the connection with the outside world's time that's been severed. Our journey now is hidden from the universe beyond the horizon. We continue it in here, in our own isolated bubble of space-time. Floating in this lightless domain inside the horizon, we feel an eerie calm mixed with apprehension. We have crossed the point of no return, and now we must face whatever comes next. But before we meet our ultimate fate at the center, we will experience other extraordinary effects of the black hole's gravity. One of those is becoming alarmingly apparent now. The tidal forces we've long anticipated are increasing with every mile we fall. Inside the black hole, as we plunge toward the center, tidal forces begin to make themselves known. Up until now, our free fall was deceptively serene. We felt weightless, as if gravity's grasp had vanished while we were in its thrall. But now the differences in gravity across our ship become impossible to ignore. We can feel the stretching unmistakably. The gravity at our ship's nose is noticeably stronger than at the tail. This differential pull grows each moment, tugging the craft more and more. It's as if some giant invisible hand is trying to elongate us, to pull us into a long line oriented toward the singularity. On Earth, we know tides as the gentle rise and fall of ocean waters due to the moon's gravity. Here, in the grip of the black hole, tidal forces are anything but gentle. The concept is the same. Gravity is a bit stronger on the side of an object closer to the massive body than on the far side. But the magnitude now is immensely amplified. We're not talking about shifting oceans by a few feet, but stretching solid steel like warm taffy. At first, we notice it in subtle ways. Loose objects in the ship start to drift toward the front, the direction of our fall. Our own bodies feel a strange sensation of pull. If we're oriented feet first toward the black hole, our feet feel heavier than our heads. There's a faint discomfort in the spine, as it's ever so slightly elongated. The ship's frame groans softly as its structure is stressed by the uneven forces. We press further inward, and the effect intensifies rapidly. There is no turning back, of course. Gravity grows stronger with each kilometre closer to the core, and with it, the gradient from our ship's front to back steepens. The gentle moans of metal turn into loud creaks and shudders. Instruments flicker. Readings go off scale. We check a measurement. The gravity at the front of the ship is significantly higher than at the rear. The numbers climb alarmingly with each passing moment. It doesn't take long for the situation to become dire. The strength of the tidal forces surpasses anything human engineering can easily withstand. In a smaller black hole, perhaps only a few times the sun's mass, this would have happened far earlier, possibly even outside the event horizon. In our supermassive black hole, it's occurring well inside. But occur it does. The term spaghettification that we discussed in theory is now becoming a very real experience. Spaghettification, the very word coined to describe this fate, comes to mind with stark clarity. It was Stephen Hawking who famously described this vivid image. An intrepid, or unfortunate, astronaut falling feet first into a black hole, stretched out like a piece of spaghetti. As gravity pulls much harder on the astronaut's feet than the head, the body would lengthen and thin into a string-like shape. Simultaneously, immense forces would compress the body's width, squeezing it narrower and narrower. Stretched long and thin, and simultaneously squashed from the sides, the astronaut becomes a strand of cosmic spaghetti. Indeed, scientists sometimes darkly joke that what remains is a sort of noodle soup of particles. In some cases, especially with supermassive black holes and whole stars, tidal forces can also lead to what's whimsically termed a pancake detonation. A star drawn in might initially be flattened like a pancake, its gases compressed violently in a flash of heat before an explosion tears it apart completely. Whether spaghettified or pancaked, or both, the end result is the same: utter destruction. Our ship, much larger and sturdier than a human body, is suffering the same fundamental treatment. The front end of the vessel is being pulled away from the back end. Bolts strain, materials deform. The vessel's architecture was never designed for such extremes. We hear snapping and popping sounds from deep within the hull, supports starting to give way. We realize that no structure can resist this indefinitely. If we were made of granite or steel or carbon fiber, it would all tear just the same under enough tidal force. And here, we are reaching those limits. The ship's integrity is failing bit by bit. Panels buckle and pop. The hull itself starts to stretch like putty, elongating into a cigar-like shape as the nose races ahead of the rest toward the unseen singularity. It becomes clear that survival any deeper is impossible. If one of us were out in space here, not that one could survive the vacuum and radiation, they would be stretched too. A person's body would first feel the pull in their feet, then their spine elongated, joints stressed beyond endurance. It would start as discomfort, then agony, then something beyond agony as the body is pulled apart. Ultimately, the forces would rip even our molecules apart. At some point, even atoms themselves would be pulled asunder. First, the bonds holding them together break, then electrons are stripped from nuclei, and perhaps even the nuclei themselves are stretched and fragmented into subatomic particles. By then, we are nothing but a hot stream of fundamental particles, a wispy thread of matter spiraling inward. Even within our vessel, which is built of strong alloys, the strain is evident. The structure creaks. The cabin itself deforms. Compartment walls up front bulge outward as they are tugged more strongly than those at the rear. It's as if some giant is trying to pull our ship into pieces, stretching the front part away from the rear. We adjust our orientation to minimize the damage, pointing the nose of the craft directly toward the center, so that the length of the ship bears the stretch, rather than its width. This aligns with the direction of stretch, and might buy us a few more moments of coherence. But it cannot stop what's coming, only delay it slightly. All around us, the consequences of these tidal forces play out on whatever matter accompanies us. Any stray bit of debris that fell in alongside is undergoing the same ordeal. A rock pulled in from the disk would be tugged into gravel, then into dust, then into atoms. Clouds of infalling gas are drawn into thin filaments, elongated threads spiraling alongside us. In fact, we suspect many of the streaks we saw in the accretion disk's inner regions were due to such stretching, matter being pulled into long streamers as it descended. Interestingly, as objects stretch and compress, they can heat up dramatically, just as the accretion disk did when being sheared. If a star were being torn right now, it might unleash one final flash of light, a brief, desperate flare of energy, before succumbing. But whatever light emerges from our breaking ship or body cannot escape now. It will not reach the outside universe. It will only illuminate, briefly, the interior of the black hole before being carried inward with us. Perhaps a brief shower of sparks flutters in the cabin as circuits fail. Even those sparks would stretch into thin streaks of glowing plasma. In these last moments, it's as if even the light around us is being pulled into lines. Our ship's forward compartment begins to tear open. Through a front viewport that cracks and then shatters, we briefly see the cabin's air explosively venting into space. Even that puff of atmosphere stretches into a thin filament of gas as it's sucked inward. Loose objects, papers, tools, bits of equipment, spill out, only to be drawn into long ribbons as well. Our view of the outside is bizarrely distorted now, as the very light itself is being dragged and smeared along with us. In these final moments of structural cohesion, the environment around us becomes truly surreal. Directions lose their usual meaning. Falling downward toward the singularity feels like tumbling through a deep, endless well that only gets steeper. If we had the presence of mind to shine a light sideways, we might see it curve strangely, or get swiftly swept inward as well. Space is no longer a stable stage for events. It's flowing like a river and stretching in the direction of our fall. Our ship holds together only a moment longer. It gives one last groan as critical supports snap. The vessel splits. Metal tears like paper. Alarms that were blaring now fall silent, as they too are torn apart or left behind. Panels, wires, and shards of structure all stream forward into the darkness, each piece elongating as it goes. We, along with them, are stretched beyond recognition. In these final, utterly chaotic moments, there is oddly a kind of serenity, perhaps because our nerve endings can no longer transmit pain, or perhaps a psychological acceptance has set in. We become strands of matter, and our consciousness flickers out as our brains are pulled apart. All that we were is now becoming part of the black hole. The black hole's mass increases by the amount of our mass and energy, and with that, its event horizon expands imperceptibly. In a sense, we continue to exist as a component of this dark entity. Our being is now merged with it. Piece by piece, atom by atom, we have been absorbed into the central singularity. The journey that began with a cautious approach through warped starlight and a magnificent disk of glowing gas now ends in ultimate darkness and deformation. But in this destruction lies an answer to what a black hole ultimately does to matter. It pulls it apart, adds it to itself, and hides it from the rest of the cosmos. Yet, even as everything familiar disintegrates, questions linger in the dim recesses of thought. Were we still capable of thought? What truly becomes of all this matter and information at the endpoint? Is it lost forever? Or is it somehow preserved in ways we don't yet understand? We have confronted what physicists call the black hole information paradox firsthand. The dilemma of whether information, the detailed story of everything that fell in, is lost for all time or somehow preserved in the black hole's memory. Some theories suggest that every bit of information about us might be encoded on the event horizon's surface as we fell, like a hologram, preserving a ghostly record that could, in principle, be released if the black hole ever evaporates. Remarkably, theoretical physics backs up this idea. It appears that the amount of information a black hole can contain is proportional to the area of its event horizon. In other words, the surface of the black hole, not the volume within, might hold the memory of everything that has fallen inside, like a cosmic ledger or holographic imprint. Our information might be smeared on that horizon now, a faint pattern in the fabric of the black hole. In our final moments of awareness, stretched beyond recognition, there is oddly a calm acceptance. The mystery of the black hole's interior is no longer academic for us. We have met it face to face. And while we cannot report back the details of this encounter to the outside world, the significance of it is not lost. We have attempted to explore a frontier that tests the limits of physical law, and in doing so, we've highlighted how much about the universe remains beyond our grasp. Now, as we become one with the black hole's core, we have effectively reached the end of our physical journey. Our mass and energy have been assimilated. Our story, at least as tangible participants, has concluded in silence. But the story of the black hole itself, and the questions it poses, is not over. The black hole holds more secrets deep inside, and what will become of it in the far future is another tantalizing mystery. Beyond this point, deep in the black hole, lies a prediction of general relativity that we cannot truly fathom. The singularity, a point, or ring, if the whole spins, of infinite density and zero volume. It's the mathematical end of spacetime, at least according to Einstein's equations. But many scientists suspect that this singularity is simply a sign that our current theories have broken down. They expect that a better understanding, a theory of quantum gravity, would replace the singularity with something else, something finite, though exotic. Some have speculated that a singularity might not be the ultimate end at all. Perhaps it could be a doorway of sorts. The idea of wormholes arises here, hypothetical bridges connecting two distant points in space-time, or even two universes entirely. Certain mathematical solutions of Einstein's equations, for a spinning black hole in particular, hint at such possibilities. Tunnels through space and time. Could it be that falling into a black hole might, under very special circumstances, send one out into another universe, or a different part of our own? It's a staple of science fiction, and an intriguing theoretical idea. However, even if such wormholes exist in the math, they would likely be unstable in reality, and no object like us could survive the violent forces to use them. So while it's tantalizing to consider that what looks like an exit from our universe might lead somewhere else, we must admit that currently it appears to be an absolute dead end, at least for anything that enters in one piece. Ultimately, after all the tidal stretching and the approach to the singularity, our physical form has been annihilated. But our inquiry doesn't end with our demise. Even as we, and all our information, reside now inside this black hole, hidden from the outside, there remains the question of what will become of the black hole itself. Black holes are not eternal, invulnerable monsters. According to Stephen Hawking's groundbreaking work, they can slowly lose mass and energy through a quantum process known as Hawking radiation. Over unimaginable spans of time, they can radiate away particles and energy, gradually shrink, and eventually vanish. How long would that take? For a black hole as massive as a star, it would take an almost inconceivable length of time, tens of billions of trillions of years, far exceeding the current age of the universe, to evaporate completely. For a black hole as large as the one we've fallen into, the evaporation time is even more fantastical, essentially eternal on human timescales. But in principle, even the mightiest black hole will, after trillions upon trillions of years, slowly fade and disappear like a final sigh. This leads us back to the information paradox. If the black hole eventually evaporates, what happens to all the frozen information that fell in? The clocks that seemed to stop, the things it swallowed, like us, that were never seen to finish falling? Does that information re-emerge in some form via the Hawking radiation? Does time unfreeze at the very end, letting the outside universe finally witness the completion of those infalls? These are profound puzzles at the cutting edge of physics, tying together gravity, quantum mechanics, and thermodynamics. From the perspective of the outside universe, our plunge into the black hole is something that virtually stops in time at the edge. This is one of the most mind-bending aspects of general relativity. To distant eyes watching from afar, it would seem as though we never quite vanished inside. They would see us slow down more and more as we approached the event horizon, our motions becoming sluggish, our clocks ticking slower and slower. In fact, at the exact boundary of the event horizon, our time, as seen from outside, would appear to freeze entirely. We would be suspended at the brink, a faint red ghost of a ship hanging there for what would seem like eternity. Of course, to us, time felt normal as we went in. It's not that time literally halts for us falling in. For us, time continues to flow forward second by second. But time is so severely dilated by gravity that, to an outside observer, our clock appears to nearly halt. Both perspectives are true in their own frames. This is the heart of relativity. Time is not absolute, and events can unfold differently depending on where you watch them from. Our few seconds of falling through the horizon correspond to an effectively infinite stretch of time, as measured by someone far away. In essence, the outside universe can never witness the completion of our fall. This concept is difficult to wrap one's head around, yet experiments and observations have confirmed the reality of time dilation. We've even seen tiny hints of it in much weaker gravity. For instance, atomic clocks on GPS satellites tick just slightly faster than identical clocks on Earth's surface, due to experiencing weaker gravity at orbital altitude. Engineers actually must account for this difference so that navigation systems remain accurate. Otherwise, GPS positioning would drift over time. Even climbing a mountain or living at a high altitude makes your clock run a minuscule bit faster than someone at sea level, simply because gravity is a touch weaker higher up. Time does not flow at a perfectly uniform rate everywhere. It depends on the strength of gravity and also on speed, which is another facet of relativity. Traveling at high speeds or living in strong gravity is like holding a ticket to a kind of time travel, not to the past, but to the future. A person who spent time near a black hole, yet somehow avoided falling in, could, in theory, return to find that far more time passed in the rest of the universe than they experienced. A famous example often cited is the twin paradox type scenario. Imagine one twin ventures near a black hole, or even just orbits it at a close distance, while the other twin stays safely far away. If the travelling twin then comes back, they might find their sibling much older or long gone, while they themselves have barely aged. Around black holes, this is not merely a thought experiment. The effect, though extreme here, is a direct consequence of Einstein's equations. In our case, we fell past the point of rescue, so there is no coming back to make such a comparison. But to illustrate, if some advanced observer could hover just outside the event horizon for a period and then escape back out, which would require tremendous power, but let's imagine, they would indeed find that the outside world had moved on vastly. Perhaps they spend only a few hours or days close to the horizon, but upon returning to distant space, they might discover that decades, centuries, or more have elapsed in the universe outside. In that sense, the edge of a black hole can act as a one-way time portal to the future. The phrase "time stands still" at the edge is a poetic simplification. Time for the falling traveller flows onward as usual, but the communication of that progress to the outside world effectively halts. To an outside observer, any process happening at or inside the event horizon appears to take forever. If we dropped a durable clock toward the black hole and observed from afar, we'd see its ticking slow down as it neared the horizon, and it would never quite tick past a certain moment. Its signals would just redshift into oblivion. Meanwhile, the clock itself, were it conscious, would tick right along and fall in. This relativity of time reminds us that time is not a universal stage clock. It can stretch and compress depending on gravity and velocity. Even light, which always travels at the same speed locally, experiences the effects of this warped time and space. At the horizon, from an external viewpoint, outgoing light is infinitely redshifted and delayed, effectively halted. The image of something falling in gets smeared out over the entire future of the universe. Only when the black hole is gone, if it ever disappears, would that image finally wink out completely. We mentioned Hawking radiation, the notion that black holes can slowly evaporate. If that is true, one might imagine that as the black hole shrinks and eventually dies, all those frozen fallers would finally complete their fall in the eyes of the universe at that final moment. Perhaps the information they carried is then released in some chaotic form through the Hawking radiation. This is one conjecture for how the paradox could resolve. The black hole eventually returns everything, in scrambled form when it dies. But this remains an open question. Our voyage in this chapter of the journey has taken us from the calm approach under starlight to the fiery accretion disk, through the one-way door of the event horizon, and into the grip of tidal destruction. Along the way, we've watched light bend into strange shapes, witnessed time itself slow to a crawl, and felt matter twisted into new forms. These experiences are not just spectacle, they are lessons about physics at its extremes. We have confirmed that black holes are both destructive and illuminating, destroying whatever falls in, yet illuminating fundamental truths about gravity, space, and time. Black holes, in fact, sit at the crossroads of physics. They demand a reconciliation of the laws of the very large and the very small. On one hand, we have Einstein's general relativity describing gravity and the curvature of spacetime. On the other, we have quantum mechanics describing particles and fundamental forces. The phenomena of Hawking radiation and puzzles like the information paradox arise from applying quantum rules to the edge of a black hole, a place of intense gravity and warped spacetime. It's a realm where our current theories strain and crack, hinting that a deeper, unified understanding of nature is required. In a way, black holes are signaling that our story of the universe isn't complete, that new physics awaits discovery when we push gravity to its limits. Our journey into the black hole has given us a first-hand encounter with these realities. It shows that even our most cherished intuitions about time and space can be upended. Little wonder, then, that black holes have long inspired science fiction and wild speculation. Humans have imagined them as portals to other universes or shortcuts through space and time, cosmic magic doors to elsewhere or elsewhen. Those fanciful ideas reflect our deep desire to find a dramatic narrative in the unknown. The reality we've experienced is in many ways harsher, a place of inescapable destruction. Yet it is also more awe-inspiring because it's real, and it still leaves ample room for wonder. Even if a black hole isn't a doorway to another universe in the literal sense, it is certainly a doorway to new physics and profound insights about the cosmos. They show us a universe where the rules as we know them reach a breaking point, and something new must take over. Something science is still striving to understand. Black holes challenge us to unify our theories, to think beyond the conventional. They highlight how much we still don't know about the fundamental workings of reality. Our voyage to the brink of the black hole has shown us luminous disks and deadly forces, and also that time can stretch and skew in extraordinary ways. Yet, as much as we have seen, much remains hidden behind the veil. Beyond this horizon of knowledge lie mysteries we have yet to unravel. The ultimate fate of whatever falls inside, the destiny of the black hole itself, and the cosmic secrets it guards. These puzzles remain, beckoning us onward, urging us to look deeper with both theory and imagination. As we conclude this leg of our journey, we carry with us a deepened sense of wonder at the strange nature of reality under gravity's supreme command. Time may stand still at the edge of a black hole, but our curiosity does not. The journey is not truly over. It now shifts to the realm of thought, theory, and future exploration. In the next phase, we will venture further into these mysteries, piecing together what science suggests about the fate of black holes and the information they contain. Our descent into darkness has given us many answers, but also left us with some of the most profound questions in all of science. Questions we will eagerly pursue as our expedition continues. A vast darkness now dominates the star-speckled vista before you. The black hole that was once a distant enigma has grown into a massive, all-consuming void, a patch of pure black that blots out the stars behind it. In the surrounding space, there is an eerie calm. No bright beacon announces the black hole's presence, only the absence of light. Because no light can escape its grasp, the black hole itself emits nothing and appears truly black, silhouetted against the background of distant galaxies. Its edges, however, do not look perfectly smooth. As you draw nearer, you notice a subtle halo around the darkness. Starlight from behind the black hole is being bent and twisted by its gravity, wrapping around to form a faint ring of light encircling the silhouette. This gravitational lensing effect offers a surreal outline of the invisible giant, hinting at its presence in the otherwise starry field. Drifting closer, you observe the halo intensify. The black hole's gravity is warping the very fabric of space-time around it, redirecting light that passes near it. If there were a glowing disk of gas orbiting this abyss, you would see it strangely doubled. The light from the far side bent over the top and bottom of the black hole, making it seem as if you could see the disk from both above and below simultaneously. But here, the black hole appears largely quiet. There is no raging incandescent accretion disk, no jets of plasma screaming into space. Perhaps this is a dormant, isolated black hole that long ago devoured its fill. In the absence of such violent activity, space around it is dark and silent. Only the gentle gleam of distorted starlight marks the black hole's silhouette against the cosmic background. In the silence of this deep space, you feel an almost serene weightlessness. Your spacecraft, and your body within it, are in free fall, succumbing to the black hole's gravity. The usual sensations of acceleration are absent. There is no floor pressing up against your feet, no jolt or shudder, only the smooth, relentless pull drawing you inward. Paradoxically, falling into a black hole feels like floating. Yet, despite the calm, you are moving faster and faster, pulled in by the massive object's gravitational embrace. The void ahead grows gradually larger in your view, expanding as you approach, though without any sound or fanfare. It's a silent ride into darkness. As you descend further, the gravitational force intensifies. You're getting closer to the point of no return. Out here in space, there are no familiar landmarks, but physics provides a boundary. At a certain distance from the black hole, stable orbits are no longer possible. You have crossed that invisible line. Now, nothing can hold you in a safe circular path. The only trajectories lead inward. If you tried to resist, firing thrusters at full power to escape, you might delay the inevitable, but only just. The pull is too strong, and growing stronger every minute. All you can do is yield to it. Your ship's engines are quiet. You save their energy, knowing there is no turning back. The black hole's gravity has you in its unbreakable grip. Gradually, the evidence of that grip becomes apparent in subtle ways. The concept of tidal force takes on a new, visceral meaning. The gravitational pull on the front of your ship, the side closer to the black hole, is noticeably stronger than on the back of your ship, the side farther away. It's the same effect that causes ocean tides on Earth. The side of Earth facing the moon is pulled slightly more than the far side, stretching the oceans. Here, near the black hole, the difference in pull is far more extreme. The nearer part of your vessel feels a stronger tug than the farther part. Right now, your ship's structure easily holds together, and you might only register this as a mild creak in the hull or a slight feeling of stress. But you know that as you venture closer, this differential pull will increase, stretching everything in its influence. If an object, or a person, gets too close, the imbalance in gravity will pull it apart, lengthwise, into a thin strand. Astronomers have a colourful name for this fate: spaghettification. For the moment, however, you remain thankfully intact. This black hole is immense, a supermassive giant, and its tidal grip, while insurmountable, increases gradually. In fact, crossing the threshold of a supermassive black hole can be eerily gentle. You could pass the point of no return without immediate harm. Were this a smaller stellar mass black hole, the story would be different. You would have been stretched and torn apart long before reaching the event horizon. But here, at this colossal scale, the gravitational gradient is more forgiving where you now glide. That doesn't mean you are safe forever, but for now, falling deeper still feels calm. You take a breath and steady yourself, knowing the true extremes lie further ahead, nearer the core. As the pull continues to increase, so does your velocity. You're plunging faster with each passing second, even though you don't feel the acceleration in your weightless state. The blackness ahead expands to dominate more of your view. The ring of faint light around the black hole has grown brighter and thicker, a visual testament to the gravity bending more and more light into your line of sight. It is as if the universe is wrapping itself around this darkness, curving the very sky around the edges of the abyss. Time itself now behaves strangely around you. You recall the principle of gravitational time dilation. The stronger the gravity, the more slowly time passes, at least as seen by someone far away. Here, near the black hole, you are deep in a gravitational well, where time is markedly slowed relative to the rest of the universe. This isn't just speculation. Even on Earth, the effect has been measured. High-precision clocks tick slightly faster on a mountaintop than at sea level, because they are farther from Earth's gravity. Astronauts living on the International Space Station also experience time at a slightly different rate for the same reason. These differences are minuscule, mere fractions of a second over months and years. But near a black hole, the distortion of time becomes dramatically more pronounced. From the perspective of a distant observer watching you fall, your actions appear to slow down as you get closer to the black hole. To someone far away, it would look like your descent is gradually decelerating in an almost dreamlike way. Every move you make, every breath, every heartbeat would seem to stretch out longer and longer. As you approach the event horizon, you would appear to creep along at a glacial pace. In fact, at the very edge, to outside eyes, you would seem almost frozen in place, hanging just above the black hole's boundary as time for you nearly comes to a stop. Your image would redden and dim, the light you emit losing energy as it fights to escape the gravity well, until eventually it fades away entirely. It's as if time stops for you at the threshold of the abyss, at least from that external point of view. Of course, from your perspective inside the ship, time feels perfectly normal. You check your instruments. The seconds tick by at 1 per second, as regular as ever. Your heart beats at its usual steady pace. You experience no strange slowing of your personal timeline, no sense of moving through molasses or anything of the sort. Local time, your time, flows onward, unaltered. This is the crux of relativity. Time can flow at different rates in different places, but you only notice the difference when comparing one frame of reference to another. Inside your ship, a minute still feels like a minute. It's only when you imagine how things look to someone far away that the weirdness becomes apparent. To you, nothing has changed. To them, you've almost stopped in time. Such is the universe near a black hole. Reality is relative. What you do notice, however, is that communication with the outside world has deteriorated to the point of silence. Earlier in the journey, you attempted to send messages back to Earth, status updates, maybe a final farewell. Now, any signal you transmit faces a nearly impossible journey out of the deep gravity well. The radio waves carrying your voice are stretched thinner and thinner as they struggle upward against the black hole's pull. By the time your signal reaches distant space, its wavelength has lengthened dramatically. A transmission that leaves your ship as a beam of visible light might arrive far away as a faint whisper of radio waves. The content of your messages, your own voice, deepens and slows, shifted far down the spectrum. Anyone trying to listen would hear your voice growing fainter, lower, more drawn out, until it slips below the threshold of detection. The signal vanishes into the background noise. You may be speaking, but no one out there can hear you anymore. You are now utterly alone. Any connection to the outside universe has been severed. All around you is the black hole's domain. The only light you receive comes from the warped, diminished glow of the outside universe that is following you down. If you aim a telescope back the way you came, you would still see the outside universe, but strange and altered. The stars behind you appear smeared and rearranged by gravity's lensing. Their light is blue shifted to higher energies as it falls alongside you, making some stars look bluer or brighter than they should, while other light is red shifted and dimmed. The entire sky behind is transforming into an ever smaller, ever more concentrated patch of illumination directly above you. Ahead of you, in the direction you're falling, toward what used to be the center of the black hole, there is only a yawning void. You face a pitch-black emptiness. No light comes from this direction, because this is the direction of the black hole's interior. It's the way to the singularity, and any photons emitted anywhere inside or ahead of you are inevitably racing inward, unable to ever reach your eyes. So, forward of your ship, the view is absolute blackness. Turning your gaze backward, toward the direction you fell from, you now see the outside universe as a rapidly shrinking globe of light. It's as though you are peering up from the bottom of a well, and the opening, the rest of the universe, is getting smaller and smaller above you. The farther you fall, the more the outside sky compresses into a tight, bright ring overhead. All around that ring is darkness. The black circular patch of the event horizon, which once lay ahead of you, now envelops your surroundings. The universe you knew has been reduced to a brilliant halo of warped light above, encircling the darkness that dominates your view. This ring of light is astonishingly intense. The photons from the outside world are piling in on top of each other, chasing you as you fall deeper. They've been boosted to higher and higher energies by gravity's pull. What was once ordinary starlight is now, near the horizon, often shifted into harsher, more energetic forms of radiation. The halo overhead glows white hot, perhaps even tinged with ultraviolet flashes or X-rays. A final cosmic fireworks display marking the boundary between the normal universe and the black hole. It is a brilliant ring, radiant with what's left of the outside light, sharpened and intensified by the black hole's gravity. It divides the universe into two halves, Above it, a memory of the world you came from. Below it, the unknown realm you're now entering. You have now reached the infamous threshold, the event horizon of the black hole. This is the boundary that separates everything you've ever known from the unknowable interior. It's often called the point of no return, and with good reason. Inside this boundary, the velocity needed to escape the black hole's gravity exceeds the speed of light, and nothing can go faster than light. Thus, whatever crosses the event horizon is irrevocably trapped inside. The event horizon is not a physical surface. It's an invisible, spherical boundary in space-time. But in a sense, it's the surface of the black hole, the last place from which light can still escape. It's what makes the black hole black. Once you slip past this boundary, no message, no light, no hint of your fate will ever be able to reach the outside universe again. Approaching this invisible frontier is, in a word, disquieting. You know intellectually that you're about to cross it, but there are no signposts or flashing lights to announce the moment. Space does not suddenly change or shudder as you pass through the event horizon. To you, it feels like just another point in space. In fact, you could cross the event horizon right now, and if you weren't watching your instruments, you might not realize it at all. There is no dramatic shift in sensation, no jolt, no flash. In classical physics, nothing special happens at the event horizon locally. It's only in hindsight, if you tried to turn around, that the significance becomes clear. Like a boat drifting past the point of no return above a waterfall, you notice nothing peculiar at the critical instant you cross over. Only later, when escape is impossible, would you recognize that the deed is done. By the time you sense any danger, it's far too late. Much like realizing the current has taken you, and the roaring falls lie ahead. Nonetheless, a profound change has occurred. You are now inside the black hole's event horizon. For an outside observer, you have effectively vanished from the universe. They would never actually see you cross the horizon. To them, you faded and dimmed, asymptotically slowing forever, just above it. In reality, you have passed through, but any signal of that crossing will never reach them. From their perspective, you are frozen in time at the edge of the black hole, your image growing redder and dimmer, never quite disappearing. To all intents and purposes, you are gone. You can no longer participate in anything that happens in the wider cosmos. From your own perspective, you can still see the outside universe, that glowing ring of light above. But you understand that those are the last photons you will ever receive from that world. There is no outside to return to now. Every path you could take, every direction you turn, will only lead you further inward. Space itself is falling inward, carrying you along like a helpless passenger. You could fire your engines, you could thrust and struggle, but it would be futile. You cannot climb out. The currents of space-time have you now. In a very real sense, the concept of outside has lost its meaning for you. Beyond the light of that halo, there is nowhere you could go that isn't deeper into the black hole. A mix of awe and trepidation washes over you. You are in a place no human has ever been, a place no probe could ever report back from. You have crossed the ultimate horizon. The familiar universe is behind you, utterly out of reach. Ahead of you lies the ultimate unknown. Somewhere in that impenetrable darkness before you, at the black hole's core, resides the singularity, the heart of this darkness, where the mass of the whole is concentrated. In theory, it's a point of infinite density and zero volume, a place where space and time as we understand them break down completely. What actually happens at the singularity, no one truly knows. It is a mystery at the edge of physics. All the equations we have suggest that our understanding stops there. Once matter, or you, goes beyond the event horizon and continues toward the center, our best theories cannot definitively describe its fate. Does the singularity destroy information? Does it punch a hole to another universe? Is it a firestorm of physics beyond imagination? Science has no clear answers yet. Here be dragons, an old map might say, the territory beyond the horizon of knowledge. Your ship now drifts in a realm cut off from everything that came before. The glow of the outside universe above is already fading, shrinking to a smaller circle as you fall further inward. The darkness ahead feels heavier, deeper, an almost tangible void awaiting you. Yet, you are calm. There is a strange tranquility here, in the silent fall. You have nothing left to do but observe and experience. The time for decisions and maneuvers is over. Slowly, you orient yourself, turning the ship, or perhaps just shifting your own viewpoint within it, so that you face downward, looking along the direction of your inevitable travel. It's an odd concept now. Downward no longer means anything simple. It's not toward Earth or any familiar reference, but toward whatever lies at the black hole's core. Still, you choose to face the unknown. With the event horizon now behind you, you are truly embarking on a one-way journey deeper into the black hole's interior. All the phenomena that have fascinated and unsettled you, the slowing of time, the bending of light, the stretching of space, will only intensify as you go further in. What will you find as you venture on? Will tidal forces begin to tear at you more fiercely? Will the very sight of the universe disappear entirely from view? There is so much still ahead on this descent, and so many questions that even the greatest minds on Earth can't yet answer about what happens next. For now, you take one last look at that dwindling ring of light above, the final glimpse of the universe you came from, framed in a halo of warped starlight. Perhaps you feel a pang of longing or loss as it shrinks and dims. But curiosity pushes you to turn back toward the blackness in front of you. There is no turning back in reality, only in thought. And your thoughts now turn to the journey ahead, into the very belly of the black hole. In the darkness that surrounds you, you begin to fall faster and faster toward the center. The pull of gravity grows stronger with each passing moment. There is no external frame of reference anymore, only the inky void and the direction of the unseen singularity pulling you in. Your fate lies ahead in that silent abyss. And so, you let yourself continue to fall, venturing ever deeper into the black hole. The story of your journey is not over. In fact, it is entering its most unimaginable chapter. What awaits in the depths, and how the final moments will unfold, remain to be seen. You press on into the unknown darkness, toward the ultimate fate that awaits within this cosmic abyss. Our perspective now broadens, moving from the realm of individual stars and their dark remnants to the grand stage of galaxies themselves. In the heart of a distant galaxy, far beyond our own, there lies an enormous darkness. It is a black hole of staggering proportions, a cosmic giant anchoring the swirling city of stars around it. Though invisible to our eyes, its presence is felt throughout the galaxy. Stars pirouette in fast orbits around an unseen center, compelled by the black hole's immense gravity. This is a supermassive black hole, a gravitational titan millions or even billions of times more massive than our Sun. These giants of the galaxy reside in the cores of most large galaxies, including our Milky Way. At the center of our own galaxy, deep behind clouds of interstellar dust, there lurks a supermassive black hole called Sagittarius A star. Sagittarius A star, despite its unassuming name, holds about 4 million times the mass of the Sun in a space smaller than our solar system. From our vantage point on Earth, 26,000 light-years away, this supermassive black hole is invisible to our eyes. Only radio telescopes can pinpoint its location in the constellation Sagittarius, where it quietly resides. It's humbling to realize that our entire solar system orbits this dark powerhouse every hundreds of millions of years. Yet we only confirmed its existence through careful observation of stars whirling around an empty space. If we could somehow view it directly, we'd see a perfectly dark sphere outlined by a halo of light, glowing gas and stars trapped in orbit around the void. To imagine a supermassive black hole, picture something so massive and dense that it has carved a permanent well in the fabric of space and time. Anything that comes too close is captured, disappearing from the visible universe. Yet around these gravitational behemoths, matter often swirls in a luminous maelstrom. Gas and dust spiraling inward, heat up and blaze brightly, creating a shimmering accretion disk that can outshine the entire galaxy. Ironically, the darkest object in the universe can be surrounded by one of the brightest lights, as infalling material announces the black hole's presence to the cosmos. Supermassive black holes have a kind of paradoxical nature. On the one hand, they are monstrous engines of destruction, capable of swallowing stars whole. On the other hand, when they are not actively feeding, they lie in quiet darkness, hidden in plain sight. For instance, Sagittarius A star is relatively calm at the moment, nibbling only occasionally on small clouds of gas or the unlucky objects that wander too close. In its dormant state, it's a sleeping giant at our galaxy's core, subtly governing the motions of millions of stars while remaining almost completely dark. Yet traces of past awakenings remain. Huge lobes of high-energy radiation observed above and below the Milky Way's center, known as Fermi bubbles, suggest that only a few million years ago our black hole blazed forth, expelling vast amounts of energy. Even asleep, this giant sometimes tosses and turns, leaving glowing echoes in the galactic night. The sheer scale of these black holes is almost beyond comprehension. The event horizon of a supermassive black hole, the boundary beyond which nothing returns, can be enormous. For a black hole, billions of times the mass of the Sun, the event horizon could be larger than our entire solar system. If one such giant were placed where our Sun is, its darkness would stretch out past the orbits of all the planets, engulfing them in its shadow. Yet, from afar, the gravitational grip of a supermassive black hole would be gentle enough that planets could still orbit around it, much as they orbit the Sun. Consider the colossal black hole at the center of the galaxy M87, one of the most massive known. It weighs on the order of 6.5 billion suns. Its event horizon is so huge that our entire solar system would fit inside it many times over. This behemoth lies about 55 million light-years away. Yet when it briefly feeds on infalling matter, it can launch jets of energy that we detect across that great distance. Such giants remind us that black holes come in a remarkable range of sizes, and at the top end, they truly deserve the name supermassive. Paradoxically, falling into a supermassive black hole might initially be less violent than falling into a small one. For a smaller black hole, the tidal forces, the difference in gravity between your head and your feet, for instance, would stretch and rip anything apart long before reaching the event horizon, a fate sometimes known as spaghettification. But for a supermassive black hole, the event horizon lies so far out from the center that the tidal forces at that boundary can be relatively mild. An object, or even an intrepid traveler, might pass the point of no return of a supermassive black hole without immediate destruction, not even realizing the exact moment when they crossed over. Only deeper inside, closer to the central singularity, would the ultimate forces of gravity tear everything asunder. In that sense, these giants are sneaky. One could fall in calmly, with the real reckoning deferred until plunging further inward. How do such colossal black holes form? It's a mystery that astronomers are still unraveling. Some believe these giants began as smaller seed black holes in the early universe, perhaps the remnants of the very first generation of stars, or dense clumps of primordial gas that collapsed directly. Over billions of years, these seeds could have merged with others and consumed vast amounts of gas, growing ever larger. Others might have formed through the merger of many smaller black holes and star clusters in a crowded protogalactic core, gradually building up to supermassive scales. The truth may be a combination of these processes, nature finding multiple pathways to create the cosmic leviathans we observe. What we do know is that supermassive black holes have existed for a very long time. Quasars, quasi-stellar radio sources, were first identified in the 1960s as extraordinarily bright, distant objects. Only later did scientists realize they were seeing the glaring cores of young galaxies, each powered by a supermassive black hole devouring matter. Astronomers have found quasars from epochs when the universe was less than 1 billion years old. These brilliant beacons, visible across the cosmos, tell us that even in those early times, black holes weighing as much as 1 billion suns were already shining ferociously. It is astonishing to think that not long after the first stars began to shine, some black holes had already grown to enormous sizes. Their intense light travelled for billions of years to reach us, a beacon from the dawn of time, hinting at giants that were already in place. Supermassive black holes often announce themselves through such light, even though the black holes emit no light of their own. When a black hole feeds voraciously, the infalling gas forms a searing hot accretion disk, and jets of charged particles shoot outward at nearly the speed of light. These jets, guided by magnetic fields, shoot out above and below the disk, piercing into intergalactic space, and a fast-spinning black hole can amplify this process by dragging spacetime around and channeling energy into the jets. Astonishingly, these jets can extend for tens of thousands of light years, drilling into the surrounding darkness. They glow in radio and X-ray light, serving as cosmic beacons that point back to the black hole's influence. From across the universe, we see the brilliant cores of these active galaxies and the geysers of radiation they send forth. They have been given names like quasars and blazars, cosmic lighthouses heralding a hungry black hole at the center. Even when cloaked in darkness, the influence of a supermassive black hole is profound. It acts as the central anchor of its galaxy, an invisible hand holding the stellar metropolis together. Stars in the inner regions speed around the galactic center under its dominion. We have observed, for example, stars near Sagittarius A star whipping around at incredible velocities, their paths looping wildly through space. Only the gravity of something unimaginably massive and compact could explain their motions. A supermassive black hole exerting its pull from the shadows. Peering into the galactic center with modern telescopes, astronomers have essentially watched an intricate ballet. In our Milky Way, One star in particular, named S2, has been tracked for years, tracing an elongated orbit around the invisible mass at the core. At its closest approach, S2 comes within just a few light hours of the black hole and accelerates to a significant fraction of the speed of light, slingshotting around the bend. Observing such a star's motion is like seeing the outline of a beast in the dark. We never see the black hole directly, but we see how space and time warp around it. It's a gravitational performance that confirms the presence of a supermassive monster lurking in the darkness. If you could journey close to one of these gravitational giants, the experience would be otherworldly. Hovering just outside the event horizon of a supermassive black hole, you would see the universe in bizarre distortion. Stars behind the black hole might smear into a ring of light around the darkness, a result of space curving so extremely that light itself loops around. Ahead of you, directly toward the black hole, there would be only an infinite night where no light escapes. Time would also behave strangely. Clocks far away would seem to race, while your own sense of time would stretch as gravity slows your seconds. It would be an awe-inspiring and unsettling vista, a cosmic funhouse mirror surrounding a void from which nothing returns. These galactic giants are not just passive inhabitants of the cosmos. They hold a dynamic role in shaping the world around them. Their gravity can stir up gas and dust, spark the birth of new stars, or snuff out stellar nurseries, and even influence the overall shape and fate of their host galaxy. They are a fundamental part of the story of galaxies. In the next stage of our journey, we will see how these black holes act as architects of their cosmic domains, molding galaxies over the eons. Throughout cosmic history, black holes and galaxies have grown side by side, deeply influencing one another. It is as though each galaxy is a living system, with its central black hole acting as a heart, sometimes quietly beating, sometimes racing, helping to drive the galaxy's evolution. This connection between a galaxy and its supermassive black hole is a delicate balance. When conditions are right, a black hole can shape its galaxy dramatically, earning it the title of a galactic architect. In the youth of a galaxy, abundant gas and dust provide raw fuel for both star formation and for feeding the central black hole. During these early epochs, the black hole may gorge on material, and in doing so, it enters a highly active phase. As the black hole devours matter, the energy released by the hot, spiraling gas can blow cosmic winds and shine as an intense beacon. These outpourings of energy from the galactic center can push away the very gas that newborn stars need, curbing the galaxy's ability to form new stars. In this way, a ravenous black hole can regulate its host galaxy's growth, preventing it from making too many stars at once. Imagine a galaxy filled with the glimmer of billions of stars in formation. Near the center, the supermassive black hole awakens and begins to feast on the surrounding gas. Radiation and powerful jets erupt from the core like a cosmic fountain. They surge through the galaxy, heating and dispersing giant clouds of gas in their path. Some regions that might have coalesced into clusters of new stars are instead swept clear. The black hole, in its energetic outburst, effectively presses a pause button on parts of the galaxy's star birth. Later, when the storm subsides and the black hole's feeding frenzy calms, the remaining gas can cool and settle back into place. Star formation might resume in those quiet pockets once again. It's a cyclic story. Periods of intense activity from the galactic center, followed by lulls of relative peace. Over millions of years, this feedback loop between the black hole and the galaxy can sculpt the galaxy's appearance and star content. Too much growth in the black hole and it pushes back. Too little, and the galaxy can continue to build stars freely. If we could watch a galaxy's life in fast forward, we might witness these cycles dramatically. In the cosmic film, the galactic core would flare brightly during active quasar phases as the black hole feeds, then gradually dim as the fuel is spent. In the surrounding disk, waves of star formation would ignite and later fizzle in response to the black hole's intermittent blasts. Spiral arms might grow with fresh stars, only to have some of their gas blown away by a central outburst, pausing the birth of new stars for a time. It is as though the galaxy breathes, inhaling gas to form stars and feed the black hole, exhaling energy when the black hole erupts and clears the cosmic air, over and over across the ages. Astronomers have observed clues of this push and pull relationship. In some massive galaxies, we see enormous bubble-like cavities in the hot gas that envelopes them, like cavities blown by a strong wind. These bubbles are believed to be carved by past eruptions from the central black hole, evidence that an active galactic nucleus can indeed rearrange the galaxy's environment. At the same time, we also notice a remarkable trend. The mass of a galaxy's central black hole is closely related to the size of the galaxy's central bulge of stars. Bigger bulge, bigger black hole, as if the galaxy and its black hole grew in unison, each influencing the other's size. This relationship hints that the formation of the galaxy and the growth of its black hole were intertwined. Perhaps in the galaxy's early life, as stars were forming in the bulge, the black hole was also rapidly accreting mass. The two processes might have been fed by the same inflowing supply of gas, or one process might have triggered the other. For instance, a burst of star formation could send gas funneling toward the center, feeding the black hole. Or an active black hole could stir up turbulence that compresses gas elsewhere, spawning new stars. The cause and effect are complex, but the end result is a galaxy and black hole that seem to have grown up together. In some ways, the central black hole serves as a thermostat for the galaxy's development. If the galaxy becomes too dense with gas and starts forming stars too quickly, the black hole's accretion can ignite, releasing energy that throttles the growth. Conversely, if star formation slows and gas cools, the black hole also quiets down, allowing the galaxy to replenish its reserves. This self-regulating dance keeps the galaxy from tipping too far in one direction. It's a gentle cosmic moderation that unfolds over eons, largely imperceptible on human timescales, but critical in shaping the grand design of the galaxy. Beyond their own galaxies, supermassive black holes can also influence their larger cosmic neighborhoods. Powerful jets from active black holes can extend well outside the host galaxy, carrying energy and matter into intergalactic space. These jets plow into the surrounding medium, stirring it up and distributing elements forged in the galaxy's stars into the wider universe. In this way, black holes act not just as architects of their galaxies, but as contributors to the environmental design of galaxy clusters and beyond. They spread the byproducts of stellar life and death far and wide, seeding the cosmos with heavy elements needed for planets and perhaps life. We find evidence of a black hole's architectural work by observing galaxies across different wavelengths of light. For example, in X-ray images of some galaxy clusters, we see enormous bubble-shaped voids in the hot gas around certain galaxies. These cosmic bubbles are cavities blown by earlier eruptions from the central black hole, pushing aside the superheated gas that fills intergalactic space. In radiolight, we often detect vast lobes billowing out from a galaxy's core, relics of jets from an active black hole that pumped energy far beyond the galaxy's stars. These structures appear as ghostly echoes of past activity, signposts that a powerful galactic engine once fired up and altered its surroundings on a grand scale. Over the lifetime of the universe, black holes have not always been as quiet as many are today. Billions of years ago, when galaxies were young and gas was plentiful, supermassive black holes were often feasting. The distant universe is lit by quasars, brilliant beacons where black holes shine at their maximum, devouring matter at a furious rate. In those early times, many galaxies had quasar hearts, blindingly bright and turbulent. As the eons passed, much of the available fuel was consumed or blown away by these outbursts. Galaxies settled, star formation slowed, and their central black holes grew sated and calm. Today, most large galaxies host a comparatively gentle giant at the core, active only when a fresh supply of gas or an unlucky star stumbles inward. Even in the present era, a dramatic event like a galaxy collision can wake a dormant black hole. From a God's eye perspective, the collision of two galaxies unfolds in majestic slow motion. As the galaxies approach, their spiral arms distort and mingle. Countless stars are tossed into new orbits, some cast out into intergalactic space. Vast clouds of gas crash together, lighting up in bursts of newborn stars across the merging galactic disks. All the while, each galaxy's central black hole drifts closer to the other, their invisible gravities beginning a delicate dance long before they meet. It will take many millions of years, but eventually, these two dark hearts will coalesce into one. When two galaxies merge, their central black holes eventually find each other. Long before they unite, the chaos of the merger funnels gas toward each black hole, reigniting them like firestorms amid the merging galaxies. This influx of fuel can turn quiet black holes into blazing quasars once more. Such flare-ups influence how the new combined galaxy forms its stars and structure. The activated black hole blows out winds that compete with the frenzied starburst triggered by the merger. In the end, the galaxy that emerges from the collision is molded by both the burst of star formation and the black hole's feedback, another testament to the intertwined fate of galaxies and their central holes. It's humbling to realize that objects as merciless as black holes can have such a nurturing influence on cosmic scales. By preventing galaxies from overgrowing or stagnating, they help maintain a balance. Without black holes reining things in, some galaxies might have become too chaotic or too bloated with stars to resemble the orderly spirals and ellipticals we see today. Yet, even as we come to appreciate the black hole's role as a galactic architect, the cosmos holds more dramatic scenes involving these entities. One of the most breathtaking events we observe is what happens when black holes themselves meet and merge. From the slow, stately choreography of galaxy evolution, our journey now turns to the violent dance of colliding black holes. Deep in the silent stretches of space, two black holes can find themselves caught in each other's gravitational embrace. It may begin when two galaxies collide and merge, each carrying a black hole at its center. As the galaxies become one, their black holes are gradually drawn toward each other. What follows is a slow, spiraling courtship as the black holes circle a common center, inching closer over time, locked in an inevitable fate. The pair radiates away energy in subtle ways as they drift nearer and nearer. For countless millennia, the orbiting black holes whisper away their energy in the form of gravitational waves, too feeble to notice from afar. Each circuit they make around their common center emits a tiny pulse that carries off a bit of their orbital momentum. At first, these ripples are unimaginably weak and spaced perhaps years apart, as the black holes orbit slowly. But gradually, the separation between the two shrinks. Their dance quickens, the gravitational pulses come more frequently and grow in strength, like a rhythm accelerating over time. What starts as a barely perceptible quiver of space builds into a crescendo as the black holes spiral inward, preparing for their final embrace. In the final moments of this dance, the subtlety ends. As the black holes draw very near, they begin to orbit each other faster and faster. What was once a stately waltz becomes a frenzied whirl. In their last seconds, they are hurtling around at a significant fraction of the speed of light, completing many orbits in just a single second. Then, in a fraction of a heartbeat, the two merge into one. All the mass of both black holes is now combined, forming an even larger black hole. In that violent union, tremendous energy is released, not as a flash of light or a burst of sound, but as distortions in space and time. That final coalescence makes space-time itself ring like a drum. The newly formed black hole quivers for an instant, sending out a final burst of gravitational waves, ripples across the cosmic fabric. Then, just as quickly, the ringing fades into silence as the merged black hole settles into its new form. These ripples are known as gravitational waves. For a brief moment during the black hole merger, the energy carried by these space-time vibrations exceeds that emitted by all the stars in the observable universe combined. Picture the fabric of the cosmos as a calm pond. When two black holes collide, they send out ripples just like a stone dropped in water. Yet by the time the waves spread outward and eventually wash over our planet, they are vanishingly faint. They stretch and squeeze space itself as they pass. But here on Earth, the effect is so slight that it alters distances by less than the width of an atom. It is a whisper in the silence, a faint ringing of a cosmic bell that had tolled billions of years ago. For much of human history, such cataclysmic collisions went entirely unnoticed. They played out in the darkness, merging black holes, sending silent waves across the universe that no one on Earth could perceive. But in the last decade, we have built instruments sensitive enough to listen to these cosmic whispers. In 2015, for the first time, scientists detected the telltale chirp of gravitational waves from a black hole merger. Two black holes, each about 30 times the mass of our Sun, had collided over 1 billion light-years away, and the ripples of that ancient event finally reached Earth, setting our detectors gently ringing. Such is the patience of the universe, that a cataclysm from an epoch before humans even existed was only heard in our time. Hearing that first gravitational wave signal was like suddenly gaining a new sense. It opened a window onto the universe that requires no light at all, a way to feel the subtle vibrations of space itself. Since that initial discovery, dozens of other black hole mergers have been heard by gravitational wave observatories. Each detection arrives as a faint rising tone, a brief chirp in the data. To our ears, if we convert the signal to sound, it's akin to a low trill that quickly rises in pitch and then is gone, like a bird calling once in the night. Through these signals, we've confirmed that black holes of many sizes are indeed out there, merging in the dark, and each new signal is like a unique note in a cosmic symphony, teaching us more about these mysterious objects and how often such events happen. To detect gravitational waves, observatories like LIGO and Virgo use lasers and mirrors along long perpendicular tunnels to measure tiny changes in distance as waves pass. When a gravitational wave rolls through Earth, space stretches in one direction and shrinks in a perpendicular direction, a subtle breathing of reality's fabric. The detectors are designed to catch that minuscule motion. It's astounding that we can build instruments so sensitive that they can sense an alteration in distance smaller than a proton across a 4-kilometer arm. To achieve this, the observatories must be kept ultra calm. They sit in seclusion, isolated from earthquakes and even distant traffic vibrations, so that no other rumble disturbs their measurements. In that engineered stillness, they wait, listening for a faint tremble from the universe. With this almost unimaginable precision, we have tapped into the cosmos's secret symphony of merging black holes. Gravitational waves have given us a new kind of cosmic sight, or perhaps more accurately, cosmic hearing. They carry information that light cannot, the detailed dance of massive objects hidden from any telescope. By listening to these ripples, we can tell how heavy the black holes were, how fast they spun around each other, and even glean hints of the direction their orbits took. We can also detect things that produce no light at all. Black holes merging in complete darkness announce themselves purely through these waves, revealing their existence without a single photon. The discovery of gravitational waves also confirmed a major prediction of Einstein's theory of general relativity, reinforcing our understanding that space and time are interconnected and dynamic. Einstein himself suspected these waves were so weak we might never actually detect them. Yet here we are, a century later, eavesdropping on events that happened billions of years ago, using instruments that act like giant ears pressed against the fabric of the universe. It is a triumph of human curiosity and ingenuity to sense the oscillations of spacetime from colliding black holes across the cosmos. As we revel in this new gravitational wave era, we are already dreaming of more sensitive instruments to catch even fainter whispers. Plans are underway for space-based detectors that would listen for waves from even larger black hole mergers, perhaps the collisions of supermassive black holes at galactic centers. One day, we might capture the merging song of black holes millions of times the sun's mass, events that send gravitational bass notes rumbling through the universe. For now, each collision we detect tells a story of drastic violence transformed into gentle ripples by the time it reaches us. It reminds us that even the most cataclysmic cosmic events can be perceived through calm, careful listening. The tale of merging black holes and gravitational waves shows that the universe is alive with motion and change, even in realms we once thought utterly dark and silent. From these grand collisions that reshape space-time, we turn our attention to a very different side of the black hole family. Not the giants that shake the universe when they merge, but the tiniest black holes that may have been born in the universe's first moments. They too hold secrets and wonders, serving as another piece in the grand mosaic of gravity's most extreme phenomena. While supermassive black holes dominate the centers of galaxies, at the opposite end of the spectrum, we find the idea of infinitesimal black holes, some as small in mass as mountains or even mere pebbles. These are primordial black holes, hypothetical remnants from the dawn of the universe. In the immediate aftermath of the Big Bang, the universe was an extremely dense and turbulent place. Some cosmologists theorize that in those first fractions of a second, tiny pockets of matter could have concentrated so intensely that they collapsed into black holes outright. Unlike black holes born from stars, these would have been born from pure primordial energy and density, scattered throughout the young cosmos. To imagine the birth of primordial black holes, we have to journey back to the universe's first moments. In that newborn cosmos, Everything was hot and tightly packed. Matter and energy churned in a dense plasma. Random fluctuations made some regions ever so slightly denser than others. If a region was sufficiently dense and small, it could catastrophically collapse under its own gravity. A black hole might spring into being out of the fabric of the young universe itself, mere fractions of a second after the Big Bang. Each one would be like a tiny fossil from creation, carrying the imprint of that fiery birth. Primordial black holes, if they exist, would be unique time capsules from the universe's infancy. They could range widely in size and mass. Some might be as heavy as a large asteroid, yet compressed into a space no bigger than a grain of sand. Others might be far lighter, perhaps with the mass of a mountain contained in an object the size of a proton. The smaller a black hole's mass, the tinier its event horizon, meaning the smallest black holes would be truly microscopic, hidden even from our most powerful telescopes. What makes these tiny black holes especially intriguing is how they would live out their lives. In the 1970s, physicist Stephen Hawking proposed a revolutionary idea. Black holes are not entirely black after all. Instead, he suggested, they emit a faint glow of energy due to quantum effects near the event horizon, a phenomenon now known as Hawking radiation. For a massive black hole like those in galaxies, this energy loss is negligible, effectively zero over the age of the universe. But for a very small black hole, Hawking radiation would be significant, causing it to slowly evaporate away over time. If a primordial black hole were small enough, it might have completely evaporated by now, dissolving into a final burst of energetic particles after billions of years of steady Hawking radiation. For example, a black hole weighing as much as a large mountain would have just barely survived the 14 billion years since the Big Bang, whereas one with the mass of a small asteroid would hardly have evaporated at all in that time. Slightly larger primordial black holes might still be around today, slowly shedding mass even now and destined to evaporate in the far future. This leads to a fascinating possibility. Could some fraction of the invisible dark matter in the universe actually be made of ancient black holes lingering from the beginning of time? It's a question researchers are actively exploring, since these primordial ghosts could hide unseen while contributing significant mass to galaxies. The possibility that primordial black holes make up dark matter is tantalizing, because it would solve two mysteries at once. Dark matter comprises about 85% of all matter in the universe, yet we know it only through its gravity. We've never seen it directly. If countless small black holes formed in the early universe and still drift through galaxies today, they could account for some or all of this missing mass. These invisible wanderers would be scattered in the halos of galaxies, including our own, subtly pulling on the visible stars and gas. It's a bold idea that connects the present to the primordial past, linking the unseen scaffolding holding galaxies together with black holes born at time's dawn. Yet it is also possible that primordial black holes might not exist at all in significant numbers. If our experiments and observations continue to find nothing, it could mean that dark matter is something entirely different, perhaps undiscovered subatomic particles rather than black holes. That in itself would be a profound clue about the cosmos. Either outcome, discovery or non-discovery, teaches us more about the infancy of the universe. The search for primordial black holes is thus a win-win for science. Finding them would help solve a great cosmic puzzle, and not finding them narrows down the possibilities for what the dark universe is made of. Searching for such tiny black holes is no simple task. By their very nature, they emit little to no light, and might be few and far between. Yet scientists are devising clever ways to hunt for them. One idea is to look for the faint particle signals from Hawking radiation. For instance, A detector aboard the International Space Station is monitoring high-energy particles like positrons that could spike if a primordial black hole passes nearby. Another strategy is to scan the sky for sudden bursts of gamma rays that might be the final gasp of an evaporating tiny black hole. If such an event occurred in our galaxy, it would appear as a fleeting flash of high-energy light, a last shout of existence from a vanishing singularity. So far, these searches have come up empty-handed or inconclusive, but they push the boundaries of observation, reaching for whispers of the universe's earliest moments. Imagine a primordial black hole, perhaps with the mass of an asteroid, but compacted into the size of a pebble, wandering through our cosmic neighborhood. As it glides silently through the solar system, it leaves behind an almost imperceptible trail of particles from Hawking radiation. We would not see it directly, but for a short time our detectors might pick up an unusual pattern of high-energy particles, a ghostly fingerprint betraying the black hole's passing. This kind of observation is at the frontier of science, a way to catch the smallest black holes by the faint whispers of energy they give off. Beyond radiation, there are other possible signs of primordial black holes. Astronomers have searched for tiny gravitational lenses, where the gravity of an unseen compact object briefly magnifies or bends the light of a distant star when it passes in front of it. To an observer, the background star might temporarily brighten or even split into multiple images. In rare cases, if the alignment is just right, the star's light can be stretched into an eerie ring around the black hole, an Einstein ring, a halo of light revealing the hidden mass. Such micro-lensing events could hint at a small black hole drifting through space. So far, no conclusive sightings have confirmed primordial black holes as dark matter, but these investigations have set important limits on how many could be out there. The idea of micro-black holes also extends to speculative realms of physics. At extremely high energies, like those achieved in particle accelerators or generated by cosmic rays, some theories suggest it might be possible, though highly unlikely, to create tiny, short-lived black holes. If one were made, it would evaporate almost instantly in a burst of Hawking radiation, posing no risk but offering a tantalizing glimpse of how gravity works on the smallest scales. So far, no such micro-black hole has been observed in laboratories. Even the world's most powerful particle collider has produced none, allaying early fears and confirming that if created, they'd vanish almost instantly. The notion underscores how black holes span an incredible range of scales, from the subatomic to the supergalactic. Tiny as they might be, primordial and micro-black holes fire our imagination because they represent extremes of nature. They ask us to consider creation itself, leftover pieces from the universe's birth, or fleeting phenomena that wink in and out of existence. In their silence and secrecy, they challenge us to expand our understanding of physics. If we were to confirm that primordial black holes exist, we would be directly touching relics of the first moments of cosmic history. It is amazing to think that the solution to the dark matter mystery or new insights into quantum gravity might come from these little grains of darkness drifting through space. Having journeyed from the largest black holes to the smallest, we see how diverse these objects can be. From sculpting galaxies to possibly hiding in the shadows as dark matter. Black holes influence the universe on every scale. Yet whether gargantuan or minuscule, black holes share a common challenge. By their very nature, they are hard to see. This brings us to the tools and techniques we use to observe the unobservable, to sense the presence of these enigmatic holes in the fabric of reality. By definition, A black hole emits no light of its own, a perfect darkness from which nothing escapes. Yet we have found many ways to perceive their presence. Detecting a black hole often means observing its influence on the surroundings, or catching the radiation from material on its way in. Over the years, astronomers have become adept at reading these indirect signals, turning what was once purely theoretical into a tangible part of our observed universe. Astronomers estimate that our Milky Way alone may harbour tens of millions of these silent, stellar mass black holes scattered throughout the galaxy. One of the earliest clues to black holes came from mysterious X-ray signals in space. In the 1960s and 70s, rockets and satellites detected intense X-ray sources in our galaxy. One source, later named Cygnus X1, stood out. When astronomers studied it, they realized it was coming from a blue supergiant star locked in orbit with an unseen companion. The companion was invisible, yet so massive that it tugged powerfully on the visible star. Matter from the star was being pulled into the darkness, heating up and emitting X-rays before vanishing. This was one of the first strong pieces of evidence that a black hole, an invisible gravitational trap, was there, feasting on its stellar partner. In our own galactic center, the evidence for a black hole came not from X-rays, but from watching stars move. Over decades, astronomers patiently mapped the orbits of stars at the Milky Way's core, using telescopes equipped with infrared cameras that could see through the dust. They observed stars accelerating to breathtaking speeds, especially one star that swung extremely close to an unseen object. The only thing that could make a star whip around like that, in such a tiny region of space, was an incredibly massive and compact object. This is how we identified Sagittarius A star as a supermassive black hole. The stars themselves served as tracers of the dark mass, their motions outlining the deep gravitational well they danced around. Beyond motions of stars and X-ray flares from accreting gas, black holes also reveal themselves in explosive transients. Occasionally, a star ventures too close to a black hole and gets torn apart in a violent display called a tidal disruption event. When this happens, part of the star's material is flung outward, but the rest swirls into the black hole, creating a sudden flare of light. Such flares can outshine whole galaxies for a short time. In recent years, astronomers have observed numerous such stellar deaths in distant galaxies, catching their brilliant flash and gradual fade as unmistakable signatures of a lurking black hole. By catching these sudden bursts of energy and tracing their fading glow, astronomers indirectly witness a black hole's presence and appetite. Perhaps the most iconic observation of a black hole came in April 2019, when an international team of scientists unveiled the first ever image of a black hole's shadow. Using a network of radio telescopes across the globe, collectively called the Event Horizon Telescope, they focused on the supermassive black hole in the galaxy M87, about 55 million light-years away. The telescopes worked in unison to act like a planet-sized lens, capturing data that was later assembled into a picture. The result was a ring of light surrounding a dark center, light from the hot disk of gas around the black hole, silhouetting the event horizon's shadow. For the first time, humanity had seen the direct imprint of a black hole. A theoretical concept had become a visible reality, a glowing ring marking where light falls into the abyss. That image of a lopsided glowing ring astonished the world. It confirmed that light does indeed swirl around a black hole just as theories predicted, and that we can actually capture it. A few years later, the same technique was used to reveal the shadow of our own galaxy's central black hole, Sagittarius A star. Though smaller and trickier to image due to turbulent gas moving rapidly around it, its appearance also emerged as a faint ring. These images did more than satisfy curiosity. They provided new measurements of the black hole's properties, like their mass and spin. And perhaps most evocatively, they turned what was once an abstract idea into a tangible picture we could behold. We have also observed black holes through the phenomenon of gravitational lensing. When a massive object like a black hole passes in front of a distant star or galaxy, its gravity warps space and bends the light from the background object. To an observer, the star might temporarily brighten or even appear as multiple images. In rare cases, if the alignment is just right, the background light can be stretched into an eerie ring around the black hole, an Einstein ring, a luminous halo that betrays the silhouette of the invisible mass. This effect, predicted by Einstein, has been seen in various contexts with massive objects. Astronomers keep watch for these telltale distortions that could signal a hidden black hole drifting through space between us and a distant source of light. Then, of course, there are the gravitational waves we spoke of, a completely different, silent way of observing black holes. When black holes collide, they announce themselves not with light, but with vibrations in space-time that we can now detect. This new form of observation complements traditional telescopes, inaugurating what scientists call multi-messenger astronomy. It's like suddenly being able to hear where before we could only see. By combining electromagnetic observations, light, X-rays, radio waves, with gravitational wave data, we get a richer understanding of these cosmic beasts. Each method reveals a different facet. Light shows us the surroundings and aftermath, while gravitational waves let us witness the collision itself by feeling its tremor. Our ability to observe black holes has grown remarkably, considering these objects themselves remain literally invisible. It has required creativity and perseverance, from patiently tracking starlight to building instruments that measure impossibly small distances, to synchronizing telescopes worldwide for a single image. Every detection of a black hole, whether through light or gravity, is a triumph over darkness. It is a way of turning something thought unknowable into something we can study and even visualize. As we refine our tools, the unseen becomes seen, and the silence becomes a story we can hear. Not long ago, black holes were purely theoretical. They arose as mysterious solutions in Einstein's equations, and even Einstein himself doubted that nature would create such peculiar objects. For decades, black holes remained in the shadows of astronomy, intriguing ideas with little proof. Gradually, however, evidence mounted. By the late 20th century, the first strong candidates were found. An invisible companion tugging on a visible star here, an ultra-dense unseen mass at our galaxy's center there. Each discovery brought these dark objects further into reality. Then in the 21st century came the crowning confirmations, the detection of gravitational waves from colliding black holes, and the direct imaging of a black hole's silhouette. What was once speculation has now been directly observed, transforming black holes from mathematical curiosities into tangible cosmic phenomena. And the journey of discovery isn't over. New instruments are on the horizon. A space-based gravitational wave detector will one day float millions of kilometers from Earth, tuned to the deep base of merging supermassive black holes. Next-generation telescopes will capture ever-sharper views of black hole shadows and the swirling disks of matter around them. With each technological advance, we peel back another layer of darkness. Bit by bit, the hidden becomes visible, and the silent becomes a story we can finally hear. Our exploration of black holes from the outside has come a long way, from X-ray flashes and star orbits to images of black hole shadows and the faint music of gravitational waves. Yet for all we have detected from afar, the stellar dances, the X-ray flickers, the ringed silhouettes, the ripples in space-time, the true interior of a black hole remains a mystery. We can map the effects at the edge, but what lies deeper inside, beyond the event horizon, is still unknown. Our journey, so far, has orbited around this ultimate enigma. Now, as we continue, we find ourselves drawn to cross that final horizon in thought, to fall deeper into the black hole's grasp, and to explore the secrets that await within its dark embrace. We drift at the very edge of the abyss, where light itself is ensnared by gravity. Even darkness is not as silent as once believed. In 1974, Stephen Hawking turned our understanding of black holes upside down. He showed that even a black hole can glow ever so faintly. This subtle glow is Hawking radiation, a whisper of particles escaping the pull, a slow release of energy into the void. Over unimaginable eons, this emission causes the black hole to shrink, losing mass particle by particle, like a puddle slowly evaporating in sunlight. Eventually, the giants that devour stars will wane, drifting toward imperceptible traces of light. When the discovery came out, many scientists were taken aback. How could something as all-consuming as a black hole allow anything to leak out? The answer lay in the strange interplay of quantum theory and gravity. Near the event horizon, Einstein's smooth space-time is restless at a tiny scale. Hawking realized that quantum fluctuations can give rise to particle-antiparticle pairs. Usually they self-annihilate, but right at the horizon, one partner can escape. Thus, his equations showed that black holes must radiate. In effect, the black hole is paying for each escapee with a bit of its own mass energy. In the emptiest void, quantum physics finds a restless dance. Space is not really empty, but a roiling sea of particle pairs that flash into existence and then annihilate in an instant. Usually these pairs cancel each other out silently, but at the rim of a black hole, fate can intervene. If a pair appears right at the event horizon, one particle can escape into space while its partner is swept inside. To break free, the escaping particle must draw energy from the black hole itself. Each escaping particle is a tiny debt, siphoning off a bit of the hole's mass. Over cosmic time, these infinitesimal losses accumulate, causing the black hole's immense shadow to slowly shrink. Crucially, Hawking's insight entwined black holes with thermodynamics. Decades earlier, physicist Jacob Bekenstein had proposed that a black hole's entropy is proportional to its surface area. Hawking's work confirmed this. A black hole has a temperature and entropy. In a sense, a black hole is a perfect black-body radiator, albeit a very cold one. This means black holes obey laws of thermodynamics. They have an entropy that never decreases, and they tend toward equilibrium by radiating energy. This deep connection suggests that the ultimate understanding of black holes lies at the crossroads of gravity, quantum mechanics, and thermodynamics, a place where new physics must emerge. If any very small black holes exist, their end would be spectacular. As they shrink, their temperature rises, accelerating the radiation. In the final moments, a black hole might explode in a flash of high-energy photons and particles. Some scientists have even looked for gamma rays from exploding primordial black holes as possible signs of dying giants. Though none have been seen, the idea remains a profound one. Out of darkness, a brilliant final burst, cosmic fireworks marking the last act of a fading giant. Every black hole has a temperature, determined by its size. The bigger the hole, the cooler it is. For example, a black hole with the mass of our Sun would be incredibly cold, only about 60 billionths of a Kelvin. By contrast, a tiny black hole is hot. A black hole with the mass of a mountain could be as hot as a star. In general, once a black hole has lost most of its mass to Hawking radiation, the radiation intensifies dramatically. In the final milliseconds of its life, a tiny black hole could unleash a burst of high-energy particles and radiation, briefly flaring to unimaginable brightness. It is as if the black hole flashes one last furious firework before disappearing entirely into its own whisper. This Hawking glow is feeble, almost impossible to detect. For a black hole as massive as a star, its temperature is far below the coldest cosmic background, making it effectively invisible to us. It would take far longer than the universe's current age for such a behemoth to evaporate. Only a very small black hole could radiate noticeably, perhaps one created in the early universe. If primordial black holes roam the cosmos, some might be ending their lives even now, releasing a final cataclysmic burst of energy. But for the supermassive titans anchoring galaxies, evaporation is like watching a glacier melt under a distant dim sun, unbelievably slow and nearly eternal. Physicists have searched the skies for signs of such miniature black holes. Telescopes look for gamma rays from exploding black holes, for strange gravitational effects, or even for faint gravitational waves. Thus far, no definitive signal has been found, which limits how many primordial holes could exist. These searches teach us not only about black holes, but also about the early universe that might have created them. If any primordial black hole of moderate mass passed through our solar system, its passage would disturb planetary orbits. Astronomers have not seen such a drama, suggesting few lurk near us. Nevertheless, the hunt continues, keeping hope alive that one day a smoking gun might appear, confirming that Hawking's theory plays out in reality. To put these ideas in cosmic perspective, a black hole with the mass of our Sun would take about 1067 years to evaporate completely. That's far longer than the current age of the universe, which is only about 10 years. For most of us, the process is effectively eternal. Only when the universe has grown cold and empty would the last black hole flicker away. These gargantuan timescales almost defy comprehension, yet they remind us of nature's patience. Even seemingly permanent structures may decay on timescales longer than imagination, leaving the universe a quieter, emptier place. Hawking radiation carries profound implications. It suggests that nothing, not even the darkest corners of the cosmos, is immutable. A black hole that was once the ultimate sink gradually releases its hold. The furthest end of the universe, when all stars have dimmed, may be dominated by this faint radiation. Even if the last atoms have decayed and all the black holes have shrunk to tiny remnants, there will still be this subtle glow, the quiet echo of what once was. In this sense, Hawking showed that the universe is self-correcting. Even the formidable dark giants return their energy eventually. What was once lost to the void is slowly given back in photons and particles, preserving the cosmic balance in a surprising way. The temperature of a black hole is inversely proportional to its mass. A supermassive black hole is incredibly cold, but a small black hole is hot. For example, a black hole with the mass of our Sun has a temperature of only about 60 billionths of a Kelvin, far colder than the cosmic background. By contrast, a black hole with the mass of a mountain might be as hot as a star. In general, once a black hole has lost most of its mass to Hawking radiation, the radiation intensifies dramatically. In the final milliseconds of its life, A tiny black hole could unleash a burst of high-energy particles and radiation, briefly flaring to unimaginable brightness. It is as if the black hole flashes one last furious firework before disappearing entirely into its own whisper. In the far future, long after all stars have burned out, black holes will dominate the energy content of the universe. Then Hawking radiation will slowly turn that energy back into radiation. Once the last black hole has evaporated, the universe will settle into a final state of diffuse radiation and elementary particles. This heat death scenario is calm and cold, but it is illuminated by the faint embers of what once were. In that ultimate darkness, Hawking radiation will be the last light in the cosmos, a gentle echo of everything that ever happened. Even in the distant future, black holes will have the final voice in the grand cosmic story, albeit a whisper. Hawking's breakthrough taught us that nature abhors eternal silences. Even black holes have a voice. They breathe out radiation, however faint, and in doing so they remind us that nothing is completely lost. But this revelation brings a new mystery to the forefront. If a black hole can shrink away to nothing, what becomes of the story of what it swallowed? How does the universe keep its record? These questions prepare us for the next journey, the cosmic puzzle of information loss. Hawking radiation offers a glimpse of light at the edge of the abyss, but it casts a shadow on another fundamental question. If a black hole eventually vanishes, what becomes of the information it swallowed? Everything that has fallen in has a story. The particles, the light, the matter, all with specific configurations and properties. Yet if the black hole evaporates, it seems to leave no record behind. This apparent erasure of history conflicts with a basic law of physics, which insists that information cannot be destroyed. Physicists call this the information paradox, a cosmic enigma that has haunted us for decades. Classically, black holes are famously simple. They remember only mass, spin, and charge. All other details, the intricate story of what formed them, appear wiped clean. This is encapsulated in the old phrase, black holes have no hair. No distinguishing features to tell one how it formed. This seems to violate quantum law. In quantum mechanics, information is sacred and can't simply vanish. Physicists have proposed radical solutions. Some envision the event horizon as a vast ledger or a hologram, where every bit of information is recorded on the surface. Others suspect that the outgoing Hawking radiation itself might somehow carry subtle clues of what went in. The debate continues, weaving together gravity, quantum entanglement, and the ultimate nature of space and time. In recent years, new ideas from quantum theory have offered intriguing hints of resolution. Some researchers suggest that the black hole and its radiation are linked by a web of entanglement that can be thought of as a network of tiny wormholes. In this picture, the information inside isn't destroyed, but sneaks out encoded in the subtle correlations of the escaping particles. These are deeply counterintuitive concepts, but they stem from the quantum nature of reality. If true, they mean the black hole's interior might be secretly reflected in the radiation field all around it. It's as if the cosmos uses a clever cheat, sidestepping the paradox by letting information bleed out under the rules of quantum physics. Some of the boldest proposals alter what a black hole's edge looks like. One idea, called black hole complementarity, suggests that information is both reflected at the horizon and passes through, with no single observer ever seeing a contradiction. Another controversial proposal is the firewall hypothesis. If information escapes in Hawking radiation, the horizon might be transformed into an ultra-hot wall of energy. Falling into such a black hole would fry you instantly. This notion challenges the old idea that crossing the horizon is unremarkable for a large black hole. The debate over firewalls is ongoing. It highlights how paradoxes push our understanding to extremes. String theory offers another wild idea. Perhaps black holes are not empty voids, but fuzzballs. In this view, the entire volume of the black hole is filled with strings and brains in a dense ball. There is no empty interior and no information loss, because everything is right there. Every black hole microstate is a different fuzzball configuration. Physicists like Samir Mathur have pursued this, showing that the classical notion of a simple singularity might be replaced by an immense quantum object. If correct, the information about what formed the black hole is just jumbled among these strings, never lost to oblivion. Other physicists look for subtler clues. Perhaps the black hole never quite forms a perfect singularity, and a tiny remnant remains at the end with all the information. Or maybe minute quantum hair on the horizon encodes it. Indeed, in 2016, Stephen Hawking and others proposed that soft quantum fields, like a faint glow on the horizon, could store information. These soft photons, or gravitons, wouldn't be visible in classical theory, but they could carry the memory of the infalling matter. This is akin to etching a nearly invisible signature on the horizon. Whether through remnants, soft hair, or subtle quantum correlations, researchers are actively seeking where nature hides its ledger. The information paradox stands as a cosmic challenge still unresolved. It highlights the tension between quantum mechanics and gravity in the most extreme environments. Resolving it is not merely a technicality. It promises to rewrite our understanding of the universe's fundamental rules. Each new insight, whether from holography, entanglement, or theories of quantum gravity, brings us closer to a solution. For now, the black hole keeps its secrets, reminding us that our journey through physics has much farther to go. Even Stephen Hawking himself ultimately admitted that his original conclusion may have been incomplete. In 2004, he conceded that information could somehow escape a black hole, triggering much excitement and fresh ideas. This illustrates the weight of the paradox. It forced one of history's greatest physicists to rethink. The episode reminds us that science evolves through questioning. What was once a strict rule might be only an approximation, awaiting a deeper truth. The information paradox, then, stands as a monument to our ignorance and a beacon guiding future discovery. Today, the black hole information paradox remains open. Research continues in several directions, from detailed quantum computations in string theory to new thought experiments about space and time. Some scientists even look to observational clues, asking if the deepest secrets might leave subtle imprints in the cosmos. But for now, it is a mystery that tantalizes both scientists and storytellers. It tells us that the universe still guards some of its deepest secrets. Yet in pondering this puzzle, we embrace the very spirit of exploration that drives us beyond known horizons. All the while, the information paradox whispers a tantalizing possibility. If a black hole somehow preserves what falls in, could it also provide a way out? Might there be hidden exits, cosmic tunnels, or gateways that we have yet to glimpse? These questions lead us to the next stage of our journey. Now, we consider wormholes and white holes, exotic solutions that hint at escape from the abyss. Wormholes have enchanted scientists and storytellers alike. They emerge naturally from Einstein's equations as tunnel-like solutions, two mouths connected by a throat. Picture space as a sheet of paper. If you fold it and poke a hole, you create a tunnel between 2 points. If one mouth sits in our universe and the other in a distant galaxy, one could, in principle, traverse vast distances instantaneously by passing through. It sounds like science fiction, but it is grounded in real mathematics. Kip Thorne and colleagues showed that if one could obtain exotic matter with negative energy density, it could hold a wormhole open and allow safe passage. This exotic matter is like an anti-gravity glue that prevents the wormhole throat from collapsing. Without it, the wormhole would pinch off faster than light, preventing any transit. So far, no known material or phenomenon can do this. Casimir effects can produce tiny negative energy patches, but they are far too feeble to stabilize a wormhole of any useful size. Thus, wormholes remain tantalizing but out of reach, a dream of physics rather than engineering. Wormholes belong to the realm of mathematical possibility. If one could travel through a wormhole, one might emerge far away in space and even time. But according to our best understanding, keeping such a passage open requires exotic matter. This strange requirement makes natural wormholes extremely fragile. Without such protective glue, any wormhole would pinch shut before anything could cross. So while wormholes captivate our imagination as possible shortcuts through the cosmos, they remain speculative and unproven. Quantum gravity hints at more wormhole possibilities. Some physicists have conjectured that every pair of entangled particles might be connected by a tiny, Planck-scale wormhole. This idea, known as ER-EPR, suggests spacetime could be laced with hidden links. If true, then the universe's fabric is subtly interconnected at all scales. Such wormholes would be far too small to travel through, but they tie the physics of entanglement to the geometry of space. It is still a bold hypothesis, but it shows how the concept of wormholes could be deeply woven into quantum physics. In theory, the classic solution for a non-rotating black hole includes a parallel universe connected by a wormhole. In that model, our black hole would be someone else's white hole, and vice versa. But this bridge cannot let anything pass, and it would collapse at the slightest disturbance. Nevertheless, it illustrates a deep symmetry. Einstein's equations naturally link black and white holes, even if unstable. The bridge exists only in the math, a tantalizing ghost of possibility that encourages us to explore beyond Einstein's horizon. Wormholes offer one kind of escape tunnel. Another is the white hole, the very opposite of a black hole. While a black hole gobbles everything, a white hole would only emit. Let us turn to this mirror image and see what it implies. Physicists have even built analogues of black holes and white holes in the lab by using fluids flowing faster than the speed of sound, or cleverly shaped optical materials. They create horizons for waves. In one experiment, ripples in a fluid could go toward a point but never return, mimicking a white hole horizon for sound. These analogues help us explore the exotic properties of horizons in a safer environment. While they are only analogies, such experiments hint that the phenomena we discuss might have broader manifestations in physics. White holes are the hypothetical opposites of black holes. They are like a black hole running backwards in time. Nothing can enter a white hole, but things can escape from it. To a distant observer, a white hole might look like a black hole at first. It might have mass and spin, a swirling halo of gas, but if it suddenly belched out energy and matter, one would realize it is a white hole instead. White holes challenge our sense of cause and effect. They would be the time-reversed siblings of black holes. Just as a black hole swallows matter forever, a white hole would eternally spew matter out, never letting anything in. It's as if you played the film of a black hole in reverse. While general relativity's equations allow such solutions, they seem unphysical to many. For one thing, a white hole would have a singularity in the past, meaning it would have existed forever, which raises paradoxes. No process in nature is known to create a white hole. It would appear as if it had always been there. Some cosmologists have speculated wildly that our own Big Bang could have been a kind of white hole explosion. In this picture, the universe's birth was a fountain of matter from a hidden origin. Alternatively, in certain quantum gravity scenarios, every black hole might eventually transition into a white hole. The idea is that when the central density and curvature become extreme, quantum effects could cause a bounce, turning the collapse into an explosion. The collapsing matter would then re-emerge somewhere, or even in a new universe. If true, a black hole is not the ultimate end, but rather a gateway to another realm or epoch. Despite these creative ideas, no white hole has been observed. Astrophysicists have not detected any cosmic object behaving like a white hole. If white holes were real, they would leave distinct signatures, perhaps transient bursts of radiation. No confirmed source matches that description. Moreover, the known laws of physics seem to forbid the formation of white holes from gravitational collapse. They remain curiosities of theoretical mathematics, reminders that general relativity's freedom must be tempered by reality. For now, white holes remain speculative, haunting the edges of theory like ghostly echoes of black holes. Our tour of possible exits raises more questions than answers. White holes and wormholes exist in the mathematics, but whether nature uses them is unknown. To resolve these enigmas, we must go further, into the realm beyond Einstein, toward quantum gravity. We turn now to the frontiers of theory, where physicists strive to reconcile the physics of the very large with the very small. General relativity, Einstein's masterpiece, treats black holes perfectly, until it reaches the singularity at the center. There, space and time as we know them cease to exist. This breakdown signals that we need a new, deeper theory, a quantum theory of gravity. Physicists are still searching for that theory, and black holes may hold the clues. One approach is string theory, where the basic building blocks of the universe are tiny, vibrating filaments of energy. In this picture, what we call particles and forces emerge from the patterns of these strings. Perhaps even spacetime itself has extra hidden dimensions, curled up so small that we don't notice them. In string theory, black holes can be modeled as tangled configurations of these strings and higher dimensional membranes, called branes. Remarkably, in certain idealized cases, string theory has been able to count the microscopic configurations of a black hole and reproduce the famous entropy formula. This gives hope that string theory is on the right track. It provides a quantum account of what a black hole really is at a fundamental level. A breakthrough idea known as holography has emerged from string theory. It suggests that the information in a volume of space can be encoded on its boundary. In a laboratory model of the universe, anti-de Sitter space, physicists found a precise correspondence. A black hole in the bulk gravitational theory is equivalent to a hot quantum system on the boundary, obeying ordinary quantum mechanics. This ADS-CFT correspondence hints that even real black holes might hide their information in a lower dimensional guise on the horizon. In other words, the universe might itself be a kind of hologram. Loop quantum gravity offers another vision. It proposes that space itself is woven from extremely small loops or threads. In such a view, the singularity inside a black hole would disappear, replaced by a quantum bounce into a new region of spacetime. In fact, Some proposals suggest the center of a black hole might eventually expand outward, emerging as a white hole. The black hole's last breath could become a rebirth, in a sense. All these theories remain incomplete, but they share a common lesson. Einstein's description of a black hole is only an approximation. As we approach the center, quantum effects become dominant. It's likely that a true quantum theory of gravity will reveal that spacetime has a different structure at the smallest scales. Perhaps dimensions blur together, or time behaves in unexpected ways. Until we can test these ideas, black holes stand as monuments of our ignorance and our hope. They point us to the edge of the known, beyond which lies the new physics that we have only begun to glimpse. More recently, researchers have explored surprising wrinkles at the event horizon itself. They propose that black holes might have a kind of quantum hair, subtle fields or excitations on the horizon that carry information. If true, these would gently break the strict no hair rule and provide a mechanism to preserve the details of what fell in. These ideas are still being debated, but they show how even the horizon itself may be more complex than once thought. Our quest for a quantum theory of gravity is largely theoretical, but observations offer hope. The ripples of space-time we measure from black hole mergers confirm Einstein's predictions to remarkable precision. Yet physicists also look for tiny deviations. If, for example, echoes in gravitational wave signals or subtle distortions in black hole shadows appear, they could hint at new physics. So far, all observations agree with general relativity, but the door remains ajar. Future telescopes and detectors may yet catch the first glimmer of physics beyond Einstein, hidden in the data of the cosmos. As physicists push forward, many approaches weave together a picture of quantum spacetime. One path is called asymptotic safety, which tries to make gravity behave like other forces at high energies. Another is causal dynamical triangulations, which builds spacetime out of tiny geometric simplices. These often reproduce black hole thermodynamics in some form, suggesting common threads. Each theory brings new metaphors. Some describe space as a woven fabric, others as a foam or network. Yet the core questions remain the same. What replaces the singularity, and how is information conserved? Black holes thus act as a focal point where every model of quantum gravity must stand or fall. Black holes serve as both the frontier and the frontier's road sign. They are where our greatest theories converge and where our imagination ignites. Having looked into the abyss through science, we now turn to see how that abyss has reflected in our stories. It is time to enter the realm of black holes in science fiction and imagination, where fact and fantasy meet. Black holes have long fired our collective imagination. From the earliest days of science fiction, writers have turned these cosmic enigmas into gateways and monsters. In countless stories, a black hole is a doorway to other galaxies, to other times, even to other universes. Sometimes they appear as apocalyptic threats, consuming whole worlds, sometimes as helpful shortcuts, whisking heroes across the cosmos. This dual nature, both terrifying and wondrous, makes black holes rich symbols in fiction. As our real science of black holes has grown, so too have these imaginative depictions, more detailed and more awe-inspiring. Ultimately, science and fiction feed on one another. Our theoretical ideas invite fantasists to dream, and those stories, in turn, shape how we view the unknown. The concept of a gravitational sink predates the name black hole. Even in early science fiction, writers imagined space as full of lurking dangers. After John Wheeler coined the phrase black hole in the 1960s, the image became central in popular culture. For example, stories in the pulp era had holes in space swallowing spaceships. As astrophysics advanced, authors wove actual science into their tales. By the 1970s and 80s, black holes were staple features in space opera and hard sci-fi. They served as dramatic backdrops where heroes confront the laws of physics itself. The interplay between science and story is wonderfully illustrated in modern cinema. In the 2014 film Interstellar, physicist Kip Thorne helped design a realistic black hole, nicknamed Gargantua. On screen, Gargantua appears as a brilliant ring of light warped around darkness, a testament to light bending in extreme gravity. The movie explores time dilation. On a nearby planet, an hour lasts decades in Earth time. Interstellar used black holes as both graveyard and gateway. It borrowed ideas from real physics, yet turned them into a dramatic journey, showing us what wonders and perils might await near these cosmic giants. In other science fiction, wormholes often take center stage. For example, in Star Trek, intrepid explorers encounter cosmic tunnels and exotic quadrants. One famous episode of The Next Generation features a ship passing dangerously close to a black hole. And in Deep Space Nine, a stable wormhole connects two distant regions of space. These dramatic portrayals are not literal science, but they spark wonder. Could we travel instantly by jumping through space? Similar ideas appear in countless novels, where a hero might slip into a black hole on one side of the galaxy and pop out in a star system far away. In this way, science fiction stretches our imaginations as it plays with the concept of cosmic shortcuts. In literature, Carl Sagan's story, Contact famously used an Einstein-Rosen bridge to send a probe and astronaut to the star Vega. Sagan enlisted physicists to ensure scientific credibility. This blending of science with story exemplifies how black holes and wormholes captivate the imagination, even in fictional form. Black holes even feature in tales of time travel. A rotating black hole, a Kerr black hole, can drag space-time around it so strongly that mathematically, time loops back on itself near the core. Some science fiction plays with this. Travelers enter a black hole and emerge in a different era or universe. In practice, such closed time paths lie behind the event horizon and likely end in destruction. Nevertheless, these ideas reveal how black holes stretch our imagination of time, mixing real physics with fantasy. From novels and films to art and music, the idea of a black hole lights creative fires. We give names to fictional black holes and chart imaginary starships diving into them. Even if these tales bend or break the laws of physics, they share one essential trait: wonder. In this way, science fiction becomes a laboratory of the mind. It lets us ask, what if, about the cosmos in the safety of fantasy. Will we one day harness wormholes, or meet some echo of a white hole? Will our telescopes or rockets reveal something as startling as the stories we tell? We don't know. But pondering these questions reminds us that the universe is bigger than our imaginations, and our imaginations are the seeds of discovery.